Już 11.
Co? Jeden, jeden, jeden. Jeden, jeden, jeden.
You're not coming home with me tonight. You just want attention. You don't want my heart. Maybe you just hate the thought of meeting someone new. Yeah, you just want attention. I do feel this right. You're just making sure I'm never getting over you. What are you doing to me? What are you doing? What are you doing to me? What are you doing? What are you doing? What are you doing to me? What are you doing? What are you doing? What are you doing to me? What are you doing? Talking in my sleep at night, making myself crazy.
Test, test, test. Jeden, jeden, jeden.
Give yourself 20.
Can't stop now, I'm flying high. Ain't no chains, ain't no ties. Let my heart take center stage. Love and music fill the page.
Good morning, everyone. We will start in 1 minute.
test. 1.
Okay, good morning, everyone. We're really starting now. So we'll have a few intro notes and then we will start the actual program. So please, how do I say this nicely? Please stop talking. Hello? Okay, thank you. I didn't think of that one. Okay, so let's get started. Hope you had a nice evening yesterday. So we have a very full day today again. And but yeah, let's start from yesterday. What happened yesterday? So we have the winners of the quiz. Didn't see you yesterday. I think at the venue. Are you here? We don't even know what he looks like. I couldn't find a picture of him. The other winner, Nikola Vasic. I don't think this picture is Nikola, but and the third winner, Ferenc Huszar, we know him. He will be shortly here with us to chair the morning session. That was the gift for him. But the other ones, you will get the gift shortly. We are expecting for them to arrive here at the venue. Okay, so congratulations for your extensive knowledge of Bosnian history and EML history and of course machine learning. Okay, next thing. Um, I'm not sure. Yeah, this is a new thing. Not really new, but so we want you to create teams and propose projects. So 4 to 7 participants from different countries, at least 3 countries. There's no exception. So you can propose ideas. So this can be quite vague or more concrete. We don't expect an actual implementation for the project, but more like for you to brainstorm and propose a plan for how something like that could be implemented. Why it's worth pursuing such a project. What has been done already in that direction. What data sets could you use? What challenges you might face, and so on. So we want you to this week create the teams. You can use Slack to find colleagues. And at the end of the school on Saturday, you will present a pitch for your project. So you'll have 4 or 5 minutes maximum to present your pitch. We will share a slide deck a bit later in the week for you to add your content there. You can also find a mentor among speakers and organizers. So yeah, really we want you to talk to each other, get to know what the other people are interested in, and yeah, find common interests, research interests. And talking about mentors, starting tomorrow morning onwards, we are starting the mentorship breakfasts. So every morning from tomorrow onwards, we will have from the speakers and organizers, we will have mentorship tables around here. So wake up early, not like today, wake up a bit earlier, arrive here at 8 a.m., look around where you see the mentorship tags, and then you can sit down and talk to experts in the field. And yeah, for tomorrow morning, we already have signed up Razvan and Federico for the, Razvan is there, is Federico around? You will see Federico anyway at the tutorial this afternoon. So yeah, just so you know, and we are still signing up other mentors for tomorrow. So I'm sure you'll have very, very nice and productive discussions. Next thing, more logistics. Tonight we'll have the first poster session and the sponsor booths presentations. So please install your posters tonight. You will be guided by the volunteers where the poster sessions happen. I shared in the Slack channel the list again with your poster IDs. Session A happens today. So if your poster is marked with A something, A number, that will happen today. If it's a B, it happens tomorrow. We have a channel, Posters Tuesday, for today. where we will enter all the posters from today. So you can vote for the best poster. At the end of the school, we will give best poster awards. And yes, of course, please do visit the sponsor booths to learn about their projects and job opportunities in case you're interested in that. As a reminder, we have the Slido and the live stream, and hello to people who are online, but also people in the room. You can also send your questions to Slido if you want that. Reminder for the lunch. Yesterday we had a bit of a crowd there. Maybe you don't need to rush to the lunch. We can have a more staggered departure. There's food for everyone, so you can stay here for a few minutes and then walk there. One more note for travel grants, whoever who received travel grants and you need to get your reimbursement, please take your physical receipts on Thursday. We'll send a reminder on Slack during lunch at the reception desk. And we will send a form as well for you to send your non-physical receipts. Okay. Finally, agenda for today. We'll have three very interesting talks and then the tutorial in the afternoon. So we'll start in the morning with Abbas with a lecture on reinforcement learning. Then we'll have Melissa on NLP. And then we have Beza on fairness and scaling. And the tutorial in the afternoon, it's on mechanistic interpretability with Arthur and Federico. Okay, I think this is all for me. So I now hand over to Zlatan to tell you a bit about our local partners this year, Ant, that we are very grateful to because they really did all the heavy lifting for organizing this post. Thank you so much, Ant.
Let's see if this works out of the box. Okay, perfect. So good start. Thanks everyone for coming, and I have a great honor to present Ant, which is the local organizer for this event. And it's not so easy to present everything in the numbers because the Ant is full of emotions and a lot of good friendship stories. So, as you might remember from yesterday, Suad mentioned that uh, Ant was founded in 2017. So far, or at least at now, we have 30 people who hold PhD actually in Ant. And when we started, actually, most of us were students. So it's really, Ant is growing with us, and also we are growing wider and deeper in Ant. In numbers, we have 130 active members, and so far we had 25 successful projects. I had opportunity to lead the project coordination team in the beginning, so I'll tell you a bit more about different projects we had. So one of our first real projects we had, and which also somehow kick-started Ant, was a STEM Youth Camp. So it was kind of initiated by the invitation or like open grant from US Embassy. And then we gathered in Ant to see how we can accommodate and how we can contribute to that goal. And inspired by such events like EEML here or Heidelberg Laureate Forum and so on, we wanted to provide a very inspiring framework or environment for young students, which are still actually high school students. And so far we had 5 of them, so it became tradition for Ant. It's a very successful project, and many of our current members, even sometimes board members, actually started in Ant through such STEM youth camps. It's usually in some a bit more remote area where students gather for several days. They have very inspiring talks from the experts in different seniority levels, very diverse experiences from physics and experiences in CERN to, I don't know, bridging the gap between, in the Cold War, between Soviet Russian mathematics and Western mathematics. So it's really, really inspiring. And we have now honor in many new projects when we read kind of motivational letters that we see that actually this project sparks students to go to study STEM and so on. Uh, to complement that and to offer students some research experience, real research experience, we also provided a student research project. So these are 4 to 6 months projects where students over the summer with a mentor do some projects, and actually we try to enable them or to provide them opportunity to present to others. So we have these common meetings throughout the project where they have to explain what they are doing to others and also to listen to others, to ask questions and so on. So we have a mix of people who do, I don't know, genetics for wolves with people who explore physics and cosmology, and so on with people who do machine learning. So it's quite nice opportunity for students also to be able to clearly communicate what they are working on, what's their contribution, and so on. And from here, we actually had so many follow-up successes where students got even PhDs. Many of them got masters and scholarships for renowned universities like TU Delft, EPFL, and so on. Uh, and yeah, we did it. This is now 5th year that we are doing this project. So I've already mentioned, we recognized the whole, so in the research landscape, so we created a BHAR directory, which kind of lists all researchers freely, so they can make their own profile and to present their research. The things are automated. It automatically pulls their new papers from databases and so on, and it also serves as kind of backbone for our next projects and our developing of the infrastructure. To boost up the BH academic directory, we organized also AI hackathon, which was really nice 2-day event. We had 7 teams and more than 30 participants. We provided them hosted LLMs, API to LLMs. We provided them API to our databases and so on. They had different machine learning academic to be honest, this is my least cited paper. So it is on archive, you can find it, but it's least cited. But we are, I think, slowly seeing there is some impact. So we in our conversation we see that some people actually read it, so which is really good. Especially some of them are kind of stakeholders, politicians, and so on. Maybe they read some part, so it's really, really good. And some of the things which we mentioned in our first paper are already kind of happening. So uh, I don't know if this was the reason, but we have also now AI curriculum at university. There were a few. We were contacted by some companies for setting up AI institute and so on. So the things are slowly moving, I would say, in a good direction. So looking forward, we also want to kind of stay and establish kind of AI institute in Bosnia and Herzegovina. We are actively working with everyone on this. Like it should be open public university, like for everyone, that people can pursue really good research. And then, yeah, if you have any ideas, any kind of wants collaboration, if you want to hear our experience to kickstart something like this in your country and so on, feel free to reach us and we'll be happy to share our experience. Thank you. Who is announcing the speaker?
Oh, this is operational. Okay, excellent. So yeah, since haven't introduced myself to the open masses, my name is Matko, and I'm the guy whose birthday, incidentally, was a part of yesterday's quiz. So yeah, that's me. Um, yeah, it's my pleasure to announce the next speaker. So Abbas Abdulmaleki from DeepMind. Uh, Incidentally, Abbas and I started our research paths as young researchers. He had a really nice PhD career where, as a part of his PhD, his research won two RoboCup, like World Cups. I took a bit of a different path, but that's another story. And then later on, we both wound up as interns at DeepMind first, and then as research scientists. Abbas is career, professional career for now. He's been mostly focused on machine learning, decision theory, machine learning, machine learning, and reinforcement learning. And some of his notable things are like he was working on DeepMind's reinforcement learning for tokamak reactor control as one of the things in the maximum purposeful learning for policy optimization. So without further ado, welcome to the project.
you don't know how good that move was until later, even until the end of the game. If you win the game or not, you know that the move is something that the first move was a good, very bad one. However, um, so basically, we talk about the technical difference between oral and and supervised learning, which is basically one give you the answer, the other one give you some sort of signal and feedback. But the most important difference between like reinforcement learning and supervised learning when it comes to building the intelligent system is that a supervised learning system can it would be impossible for the human to actually take that move. Um, and and basically this is the promise of reinforcement learning, that not just replicate the human intelligence, but to discover new knowledge. Um, so why is that? Where this ability comes from? Um, it's because for many of the most important problems that we're facing, generating a perfect solution is incredibly difficult. Like, it takes a few human years of study to maybe find a new proof for a specific hypothesis. But often verifying first challenge that we have in reinforcement learning is basically the problem of delayed rewards. So, like, imagine that you win a game, or like of chess, and you wouldn't know which move was the one that led to victory. The same of writing the proof for the math. Like, you start with some hypothesis, um, and then you keep changing your hypothesis, and then you don't know that it was the correct one, like which one basically take which smart calculation your proof like basically take you to the answer. Um,
And this is very hard in particular for the learner to figure out, like what action was responsible for the success. And this is something that we call the cradle assignments. And much of the research, like in reinforcement learning, like in Q learning value function, is basically for figuring out this problem, which we call cradle assignment, which we'll discuss later if we have time. The second challenge in reinforcement learning is the exploration problem. So like a classic basic example is that imagine you're in a giant maze and there's a very big treasure hidden somewhere. And you don't know where it is, but you will get reward when you find it. And every other step gives you nothing. So now the question is, how would you like explore this maze efficiently? Also, on the other hand, I tell you there's a treasure. I don't tell you how big it is. Maybe there is like a small pile of coin that you find, and you think that's the treasure. Maybe there is bigger. The question is, if you found something, should you stop exploration, or should you hope that there is another like a bigger reward you can gain? And when we want to people will say, let's scale up reinforcement learning, usually they mean how can you parallel the setup so you can generate more and more data. That's basically the scale up part of R&D. You need to tackle the sample allocation with more data. Normally what people do is build a simulation and then we try to make the simulation as close as possible to the real system, and then the simulation can. The other challenge is actually like is a bit subtle, but it's not like when we say that, like if you just define the reward, it's not really just define the reward. Like defining the reward is not easy, because your AI system will achieve exactly what you reward and what you meant. And this happens like in a lot of, I don't know if you heard that, or the reward hacking happens. For example, like I'm working on some walker like in simulation to, for example, get to the end of the arena as fast as possible. And then the day after I come and see it, the walker learned to fly. It's not supposed to fly, it's just like a physics bug. But then the RL system just wants to get you as fast as possible to the end, so it just makes it fly. I didn't tell it like this. So basically like reinforcement learning is actually really good at finding the bug of your system. It's like really good at that. and which we call like reward hacking. And it's extremely difficult, especially like the more you want to make it easier for the agent, like we call it like a reward shaping, the more this problem will come up. So the simpler your reward usually is, like that you can give something like a sparse at the very end that was success, that was failure, would be better. But yeah, this is the trade-off because you want to also like make the agent to understand that. By the way, there is a problem with this image. There are three groupers. They're both AI generated. So, all right. So this is our we said what are what are the challenges. But even with all these challenges, let's look at some of the breakthroughs where basically happened via RL, and maybe we can talk a little bit about like. And I think even the term of the deep reinforcement learning was coined after this video game success on Atari. Oh, this is going to be challenging now. Yeah. Oh no. What? Okay. So yeah, like I just want to show you, like this is the one of the iconic videos for deep reinforcement learning. It basically shows how this starts, like it shows all the process that it starts from playing randomly, and then it slowly learns how to. This is like a random agent. And then learns how to just return the balls. And then at the end, it discovers this tunneling through the bricks strategy. So basically, you can see how slowly from nothing learns like a very basic just returning the balls and then finding like a winning strategy. Yeah, I needed to show this because it is like, I think back then was very surprising that it figured this out. Okay, so this basically is one of the examples we said that RL can find you something that you don't expect, like find you unexpected solutions that even the human, it cannot like figure it out, and then the reinforcement can figure it out. So how did it work? So basically, what was the reward signal was very simple, so very intuitive. It is a game score that it was provided frequently and continuously. So it would make the feedback much less like delayed. Um, and because like basically whenever in the breakout, for if he hit a break, the brick, it will get a score like right away. So then AI would quickly know that was a good action. So that's how the kind of, and then there is something about Q learning that we can talk about later, but this kind of continuous getting a reward make it easier for the agent to learn. The exploration, because again, similar way, because the reward was constant, like you getting like, as for every single action it would get some signal how good that action was. It made it easier, so it would give you just this natural like guidance that basically you would guide the agent towards the useful actions, like we call them like reward shaping. Let's put it that way. And also, of course, how it tackled the problem of data efficiency is against one of those examples like back then that is a scaled up reinforcement learning that basically they use simulators with the data collection, so it could collect a lot of data and play thousands of games. And basically how it looks like, you can see on the right, you have this neural network, and you get the pixels in, and then you basically get the actions out. And the output of this network is that for every possible action, so I think it's 21, so in Atari I think you have 21 possible actions. For every possible action, you get some score that how good for that pixel that action is, what's the probability of that action, and it will choose that action. Okay, next. So the second application was basically after the like basic video game. So when that's solved, there are other video games that was solved, but usually the first one is the one that make it to the press. But then the second challenge that I think many people were impossible to learn with AI, because Go has a very large state space, like in terms of all the possible states that the board can have. It has, I think, 361 possible move every time. So if you multiple, like 3061 factorized, then it's like, yeah, basically there are more possible moves playing Go than there are atoms in the universe. And because of that, that was a very big challenge. Like many people would say it's impossible. You can, and even like Go player usually like would say that you play Go with your heart, with your soul, because it's very difficult to play with your logic, given like how many possible like kind of states has. Even Go players will take it like another level game. It's not like a chess, not logical. It's like you need to play with your heart. And again, like how it was solved. So there are different versions of basically AI that solve Go. Like one of them was with a bit of human data collection and then RL, but eventually the one that we call it Alpha Zero, Alpha Go Zero, like was the one that basically start from the random play. It's basically it learned by playing against itself. So every time it would the AI would get better and would beat itself and gets better and better. So it's called self-play. And it resulted in like a superhuman performance and actually discovery of some novel tactics. So I don't want to. So basically, I think what it was interesting, because I think this is the bit that the move 37. I want just show what happened, how surprised commentators were when the AlphaGo, when it was playing, did that. So it's showing us. So you see, people are basically surprised, like unthinkable, like. The other person that, oh, this is surprising, and everyone say, oh, it was a mistake. You see, So I just wanted to show, like, it was really surprising move. When it moved, like, all the people that were basically watching say, oh, that was surprising, unthinkable, like, AI did a mistake, it was stupid. But then it actually happened to be, you see, like, everyone basically was making these comments that that is not, is just, it's very unusual. And so yeah, so this is one of the moves that, again, is another thing that AI can find you something that you wouldn't expect, even humans. And later, like, it was basically the winning strategy, the winning move. So then later when they were studied at the end of the game that they won, they said that actually was the move that changed the course of the game, that the AI could win that game, and which they call it move 37, that then Go players still, like, then when they study about it, and basically it captures that moment that, again, like, AI can surprise like humanity because it can find something beyond human knowledge. And basically the same thing happened after with chess. Like, chess also was completely solved. Also, like, it found really unexpected moves, and many chess players like use AI to study like a novel strategy in chess. So how did it work? So for basic Go and chess are very similar. So the reward signal is very simple. Is very very clear. You basically will get a win or lose signal, and it's the clarity of maybe avoids a bit of reward hacking. I mean, is debatable, but yeah, it's better for avoiding reward hacking. And the exploration here was solved via self-play. So you start with the random agent. You don't put the random agent to play with expert. You put the random agent to play against itself. So you give this kind of natural curriculum to the agent to slowly, like, improve. So you solve the exploration with self-play. It creates like a better version of it constantly, and make it to be better and better. And how the data efficiency was solved? It was solved, like, again, via massive compute. And yeah, it would allow, like, basically it would play, like, in one day it would play more than, you know, a human would play in a lifetime. So again, as you can see, like, as we are going, you see that the data in efficiency is the one that has a very, like, so far very similar pattern across all the applications. Basically, just you make your system faster, parallelize, compute, scale your system up. Is it like an engineering fit to basically solve the data efficiency problem? Okay. So far what we showed, the applications were like video games, boards, but we also had some interesting results in the physical worlds where AI was used. And basically there are some examples where you could teach the AI like a dexterous skills that needs like a incredible coordinations and adaptabilities. Like basically two examples was solving the Rubik cube, or like robots that playing the soccer. We'll see some videos of it in a bit. And again, all these skills, even the one that in the physical world, they all were solved in simulation first. So they were simulation, they were solved there, and then they were transferred to the real system. So maybe the first example that was very interesting was the OpenAI that is solving like Rubik's cube. So this is this one of the tasks is very difficult to demonstrate by human. Like you cannot. I mean, even now today, I'm not sure how we can really demonstrate it, like by humans. So it's very difficult. So it's one of the things you really need the AI, like something that learns by itself. And basically how that was done is that it was like this huge like simulation system, and a lot of domain randomizations happen. So like in the simulation, they will change the colors, they will change the physics, like make the so probably they tried the robot, like for example, they would know how to block, uh, and the same. This basically was was trained person simulation. Uh, Even I think there was a 2x2 version that again they will learn some coordinations. You know, they do. But like for example, these blocking behaviors, they were really quite cool. You know, that it learned, you know, to do kind of blocking and stuff. But this also was a huge effort. Like these robots would keep breaking, uh, and it was like, yeah, like, and they had all names with Messi, Ronaldo. Um, yeah. So, oh, okay. So basically, like, how key in robotics is basically solving the sim to real gap. Like that's basically the key. And usually what happens is that it's a very like heuristic process. Um, you build a simulation, you train something, you deploy it on the robot, doesn't work. You look at it, you say, okay, probably it doesn't know how to do this, it's not close to the reality. Go back to sim, make the sim better, use domain randomization, train another one, go back to real. This is like basically this iteration of going from the sim to real and then make the sim as good as possible to finally do it. Um, and yeah, basically like the sim to real problem is the main thing to solve when it comes to robotics. Okay. Application 4 is like basically fusion control. So it's actually really interesting uh, application. That's so I don't say if you I don't know if you know about nuclear fusion. So like you know in stars and in sun there is this and that needs to basically the key of getting that reaction is reproducing the same as in the sun. So basically how hot is if you make that hot and usually you can see is like half a second perhaps or 1 second something like that. So you need to keep it 1 second. So that was is done and it's not only like this shape. So when it comes to the fusion control, um, they believe that different shapes have different properties for reaction. So there are like a lot of other shapes. For example, you have droplets. For example, this droplet is it's not possible to solve it at all with linear controller. It's just the theoretic is impossible. So you need to have some sort of neural network. As far as I know today, maybe there will be a linear controller that can solve this, but as far as I know, for now it's like that. You have like negative triangularity, you have like a snowflake, you have elongated class. So you have all these different shapes, and then you want like an AI agent that you just give it the shape, the target, and whatever it is, and ask to basically control this plasma in that target shape. And that's basically what was done with this work on RL. And basically how it worked is that the reward signal was basically a continuous signal. You get how close your plasma at any time is close to a target shape. So you would get a target shape. So you could see how close it is. So you get the immediate reward. And in terms of exploration, again, is on easier part of exploration because your reward is shaped. So every time you get a signal, so you know where the how good the AI is doing. In terms of data efficiency, so it basically we had a very good simulator. It was like a collaboration with EPFL. So they were building a really good simulators, and the tokamak also was at EPFL. So it was needed that collaboration to make this happen. Yeah, but like a few things like to say like during this project, for example, like it was very important that the neural network is small enough so it's fast enough to give action. I remember like we couldn't go more than like a 2-layer MLP, because if you go more than 2-layer MLP, it wouldn't be fast enough because you need I think it's 1,000 hertz or something like that, like in terms of the number of actions you need to send in each second, more in thousands of actions. So like there are a lot of challenges to get this work. So when you come to RL and like real world, you have a lot of limitations that you need to basically get around it. And we were very lucky that seemed to real gap we could solve it. There were a lot of gaps, but we could make it better and better like at every try that we did. Yeah, so again, this one seemed to real good simulator, and then basically good engineering. It was a lot of engineering work which made this happen. Okay, so yeah, so we had this, and then the application 5, I think probably is the final application, but I think it's the most important one, perhaps, AI assistance. So when it comes to AI assistant, like in language model, like the challenge is that like there is no game score and there is no simple objective, right? And the goal is very high level, to be helpful, honest, harmless, and to be aligned with human values. How would you reward that, right? It's very high level. So it is, to be honest, much harder than like a problems we have like in Atari or even like in the Fusion, because there at least your goal is clear. Here is like make the LLM to be aligned with the human values. It's like quite it's not very clear. So and this basically done with a technique called reinforcement learning from human feedback or RLHF. And it's again like it is another application of the core principle of RL that RL works when the verification is easier than generating the right answer. So how it works is that the AI generates like a couple of answers to a question or more, and the human doesn't write a better one, but it just need to pick one which answer they like more, like some human. And this basically preference, we call this preference data. So you collect this data, and then you train a reward model somehow, and then you can use now you have a reward model that RL needs, by training on this preference data, and now use that reward model to train the LLM. So a still reward is there, but basically the challenge of RLHF is that train that reward model, how you do it. And then the basically the key is collecting the good preference data. That's the key. And the rest is really the same, even easier than typical R that we do. So the challenge is the reward model. Why it's challenging is because, again, it's just not clear, right? So you get a rater. Sometimes, some raters just, they're not in mood or something, and they're not really gonna reflect the human values. So they might sometimes just pick random preferences because they're not in mood, let's say a rater, a human rater. Or sometimes we know that a human rater will use another AI. Like, for example, you want to collect data for a Grok, and they use ChatGPT to rate the answers just because they're faster. So it's a very difficult process to collect that aligns with the human values. It's a process, and it's not on the algorithmic part, but more of like on the technical part of the things, how collect that data. So yeah, just to summarize, like the RLHF process is that you take your model, you prepare some prompts. For those prompts, you generate a couple of responses. You get the human feedback, and then you bring back that data. You train a reward model, and then now that you have a reward model, you can do RL as before. Okay, so how did it work? Is that basically, so the reward signal, as we said, it's a human preference data, and if it is correct, it is actually rich and dense, if it is correct. And how data in efficiency solves, so one of the good things about LLM, which we'll talk a bit later about, is that LLM is actually gonna help you to solve the data in efficiency, because unlike many other applications, all the other applications I showed you before, they all started from scratch. So you start from like a neural network, initialized near zero weights, and then you get what we saw, all the other applications. But the RLHF application other is not like that. So you basically start with a pre-trained system that it already knows about a lot of things about the world. It just doesn't know our values, but it knows like a lot of things. And all you need to do is basically to fine-tune it a little bit to steer it towards the goal. So they are inherently and naturally are data efficient. I think LLMs maybe probably the pre-trained like LLMs are maybe only system that they are naturally data efficient when it comes to post-training or fine-tuning. And how the exploration happens, again, this is guided by the pre-trained models. So whenever you ask LLM, even the pre-trained one, it's gonna give you some answer that makes sense. It might not be the best answer, but makes sense. So if you sample enough, like 10 of these, one of them gotta be all right. So the exploration is solved again because of the pre-training. So in AI assistant world, there is another application for RL that is the basically learning to reason. So the idea is that so whenever you pre-train a model, which we call like a next token prediction, it literally learns the distribution over this next possible token. So it's really guessing. Like whenever you just you give an input, it guesses what is the next just sample from, right? And now the question is how we can make that instead of just guessing, make the AI to learn on its own, to think through the problem. So it can actually learn that if I ask this question, what is this step-by-step chain of thought that it will help itself, the model, to give you the correct solution and find the answer. So basically, at the end of the training of this LLM for reasoning, the the LLM just doesn't only basically know, like similar to pre-training, doesn't only know like what would be the right answer, but it knows how to find the right answer because it learns to do this chain of thought. And how it works is that you basically just give the question prompt, and then get this chain of thought, and then the final solution because of that chain of thought. And then you reward the whole process, whole generation, based on that final, based on final answer. So if it's correct, you say that that was the right chain of thought. If it wasn't incorrect, then it was wrong. And that's basically the reward that you have and you need. Like, it was success, it was failure, and then you can use RL to basically train the model to do that. One good example of it, I mean, there are a lot of examples. This aha moment, probably you all heard, or some of you heard. But I think it is I just took the DeepSeek R10 like paper. Just basically shows that after the reasoning, the agent thinks that one way to find the solution is that in the middle of the reasoning it says, wait, that's an aha moment I can flag here. So this is again like, you know, you don't know what is, this depends on the system, of course. Sometimes I say the reasoning, like we call reasoning, but another way of looking at it is that you make the system to hack itself, like kind of, it figure out what should I be the input so it can find the right answer. So this is basically, you give the question, and then it starts to think, and then in the middle of the thinking, it says that too, and perhaps it helps it to find the solution in some way. You know, we also do that. I mean, it is probably in the human data, of course, but it's interesting that it also picks it up here. So how it works? Basically, so the first thing is that, again, the key of getting this to work is that you start with the pre-trained model. So that's the key. Why? Like a pre-trained model like can give you always like some, when you give it a problem, it's gonna give you some answer that makes sense. And then you need to pick some, so the other basically challenges here is that you need to pick the task that you can verify. So that's basically very important. Like when like one of the challenges of reasoning is that, okay, fine, you can give a reward, but what can we reward? For example, like it's very difficult to reward, you know, like that painting was good or bad. Like it's just very difficult. But math, for example, is something is ground truth. You know that if the final answer to a math was correct or incorrect. So that's something that usually people use for training like reasoning models. The other thing is the code generation. Like you can use compiler to see if that code got compiled or not. It got compiled, you get a reward of basically +1. If not, you get negative. So it's very important to pick these verifiable environments. And what happens is that we hope that if you put this model to learn reasoning in math, in coding, then it also will generalize to learn reasoning for, you know, a political debate. So this is the hope. So you hope that you put these things, and then it will just generalize to other things. Maybe you can say that if someone is good at math, it might be a good at I don't know, debating. But this is basically the reason that it works. So the challenge is that you pick these environments. The more verifiable environment you have, the better it is. And there is a lot of research on that what are these verifiable environments? Or how can you do reasoning with environment that you cannot verify? This is like also another research question. And again, the exploration was like solved or simplified by just starting with a pre-trained model that already knows how to code or do math. So this model already knows how to code or math, so you just can get an answer all the time from them. And in terms of the data efficiency, so how it works is that it's usually like the data being collected, like the prompts are generated beforehand. So you generated the prompt, like some question for math, some question for code. You can auto-generate them, like, you know, it's usually offline, that prompt. And then in the online part, when you prompt the system, you basically use, again, a lot of compute. And you can solve the data inefficiency there by using a lot of compute. Okay, so yeah, we talk about ORL, we talk a little bit about the challenges, we talk about the applications in past decade. I guess like you all like keep hearing about reinforcement learning, like, you know, that is gonna be the frontier now to push the AI further. You hear more and more that, you know, this system managed to think 2 hours, 3 hours. It's kind of makes sense that you need such a system that can explore and learn, and going to be very powerful. There's no doubt about it. But why is now is this is more important than before? Like why it is now is actually, you know, I think it's probably it's first time that you use like a RL trained model as a product. You use that as a product. I don't remember like before AI assistants you had any other system that someone would claim, oh, actually the dog, bipedal dog was trained on the sim2real and then was used as a product. But I mean, that's exception. But basically why it's now RL is actually so useful that you can put it on the hands of millions of people and you can train a model with it. This is pretty a successful story for reinforcement learning, which we didn't have before. Before was more of the research, you know, reinforcement learning. Like now it's actually like build good products. There are 3 basically powerful forces that came together. I go from least important one to the most important. No, actually, they are shuffled. Okay, so, but the least important one is probably advanced algorithms. The second important one is the massive compute. I think that now you can run a lot of like experiments and generations on these language models. And most importantly, I think what making now many R applications works is these pre-trained models. Like, because the exploration usually was a very difficult problem. You know, like the fact that you expected the agent go play Atari without knowing any rule about Atari before, or not knowing any strategy about Atari, it just doesn't make any sense. Like you as a human don't go and learn a new game without knowing anything. Now you have these models that you can start with that they actually know about the world, about the games, about everything, and it's much easier to now learn a new thing because of all the knowledge that are these pre-trained models. And I think this going to be the most important reason that RL will eventually be like working, because it can solve the exploration problem, it can solve the rewarding problem even. Like once these models get better and better, you can use them to give you the reward. They eventually gonna basically, I think, solve many of the problems that we talk about, challenges that the reinforcement learning like have. Okay, so it's not end of the talk, but it's end of the first part of the talk that I just wanted to go from like a high level intuitive part of RL to just give you some that hopefully excite you a little bit about reinforcement learning. Basically, yeah, so RL is basically a powerful paradigm for learning from the consequences of the actions. And its power is coming from for solving the problems where it's easy to check the success, even if the path to the success is hard. We've seen that there are challenges like delayed feedback, exploration, reward hacking. The breakthroughs that we have seen today are the result of combining some core ideas with massive simulation, clever algorithms, using foundation pre-trained models, and bringing all this together are the reason that we see some breakthroughs of using reinforcement learning. Okay. So I now go back to the question that I asked at the beginning, that how do you create something that can truly learn? I said 2 paths, so probably you all agree that is not really like one single bullet point. It's like a combination of things, and usually really depends on the task. Still, I think for fusion today, still you just can do really RL. Like you cannot demonstrate like optimal controller to the fusion. And still you need to do it from scratch perhaps. Still you need to do it like with reinforcement learning. So how to basically build the AI system? You just want to be pragmatic like about it. Like basically just see where you can collect data, where you cannot. For example, for robotics today, like the arms, the recipe is a lot of data collection via demonstration because it's possible. So basically, it's possible to do that, to go and collect data and do supervised learning. But usually the recipe is working these days. Yeah, do supervised learning, pre-training, and then do reinforcement on top of it. Usually, this is the recipe that's working. Then I expect that will be the recipe that will work also in the future. Right. Okay, maybe are we done? No, sorry, I think I have half an hour, right? Okay. Maybe give you like 5 minutes break if you have any question. No, yeah. No.
Okay, so maybe we should turn it on. Oh, it works. Awesome. So you mentioned reinforcement learning in the context. Okay, I got to be honest with you, not very directly linking it, but with reasoning models and stuff like that. I always saw that as being very dishonest in the sense of it's doing anything to have to do with reinforcement learning because it's still in context learning. It spews everything out and then puts it back into the context, so it's still in context learning, but it's trying to simulate something that PPO and GRPO have sort of implemented, and that's the issue that I have with these recursive language models that are, generating token by token. They can't know that the step that they're taking inside of their very, very large exploration space is the right step to do because they're generating it token by token. So is this some sort of architectural problem that we really need to look into? How language models that we, the popular ones that we're pushing right now are having issues with, and we need to rethink that? Or should we just, keep on lying to ourselves that this is some sort of, we're always trying to, especially with PPO and GRP, we're trying to, approximate how some specific step in the and last steps was good. There's no reward function. What you place examples of chess and all of these, Tetris and stuff like that. We have a constant feedback loop that is very deterministic. There's the score, +1, -1. So is this a more architectural problem, or how do you see this?
Yeah, I think you're right to say that it's not really RL, it's a bandit RL. So like RL start with bandit when you basically take an action and then you see the result immediately and then you optimize it. And yeah, the real power of reinforcement learning will come when you actually do the create assignment. I agree with you. And still, we don't see that yet, in language models, or maybe there is some lab is doing it. Maybe they just don't say it. But the truth is that we call it RL because we eventually want to do real RL, and because like the ultimate potential of RL will be in that setting that you can do proper credit assignment. And actually, when you do it, it will be very, very powerful, far more powerful than what we have today. So it's so it's like let's say that we are seeing into the future is going to be RL, like in the way that, or maybe again it might be some lab or it's doing, I don't know, you know. So
That's why I'm asking, is it an architectural issue? Because you're now generating token by token. Maybe I've probably blown everyone's heads out with the whole diffusion text models thing. But that's an alternative representation, alternative architecture that can give you a bird's eye view of the problem. Maybe that's something to look into.
So I mean, we can talk later about it. The thing is that, like, the way that we know, like, I don't think it's an architectural problem. It's more of like the algorithms that we have to do this kind of perfect credit assignment, which we say Q-learning. They are very unstable, and these models, like with billions of parameters, are already like on the edge of crashing. And still we don't know, for example, how do proper pre-training for learning a Q function. Let's say there's a lot. I would say it's an algorithmic issue. It's just a difficult problem. You know, I don't think so. It's like I mean, architectural limitations. It might just bring you some challenges, but probably you can figure it out, like how to do it. But I would say it's like more of the. It's just a difficult problem. And maybe people tried, it didn't make a difference as well. Maybe this is also another thing. Maybe it's just, I know many people try to learn value function and stuff, and then the reporting didn't make a difference. And then when it doesn't make a difference, you go back to the simpler setting. So I think it will eventually happen, and it should happen if you want to really unlock like the real potential, because this Q learning and credit assignment learning is very powerful in the sense that it can stitch the trajectories together. It can really, if you really find like the reason that all this like unexpected strategies that we saw in some other applications, the reason that happened is it was mainly because I think this value learning and Q learning. Because that's the one that's gonna like connect and stitch the trajectories together. Which the current one we do now with like a bandit setup, it won't. Yeah, I would just say that it's a hope for the future.
So I have a question here.
Oh, yeah, sorry.
Okay, so in LLMs, we know that they're trained for reasoning nowadays, and so in my experience, I have experienced that the reasoning traces are sometimes longer, sometimes shorter, so you can't really control them. And I was just wondering, this is similar to reinforcement learning exploration problem, and I was just wondering how we could, think of this problem as a reinforcement learning problem and try to control these reasoning traces.
Yeah, so I think like, again, like if you go back to the basics, like for example, like Q learning with discounting factor, right? It basically by definition is finding the optimal path that takes it, like finding the shortest optimal path to solution. That's the definition of Q learning. So if you do it, the Q learning, you will get the shortest trace, shortest path to the solution. So I would say it's again like some algorithmic choice. I mean, they understand the path just as much as, they just sample like, a generation, and then one goes, and then they basically fit that back. So yeah, like, I don't think so they really understand, like in the sense that, again, like if it can find some weird character that for some reason would activate something in the network that give you your rights, which is gonna use that character. So I would say more of hacking. You can actually say it's hacking itself, like, I mean, it's okay. Maybe we reason and hack ourselves too, right? Maybe we just, maybe they are the same thing. But I don't know. Like, if you're looking for understanding the sense that, like, how we understand, I don't think so. Like, if we just figure out, like, what is that token, that golden token that if I give as an input, it will activate something, and then that something give you the solution, right? That's what it's gonna do. Okay.
So I want to ask one more question.
Yeah.
If you have time.
Yeah.
So from your talk, I understand that you're very bullish on LLMs, and you were mentioning reasoning, like that LLM learned the world model. But I want to push back a bit on that.
Yeah.
And that's that, like, I don't feel that they really learned the world model. They have something, but I wouldn't say that's a world model. So I'm interested, what do you think about that? Like, how bullish you are on the LLMs, and like from the perspective of some researchers in the field, like, I don't know, for example, Jan LeCun, he says that he moved on from LLMs, and that they cannot learn the real world model, and for example, that like text is not high enough bandwidth of information. So for example, from videos, you can get much more information, and they don't act in a real world. So how, like, what do you think about that?
Right. I mean, to be honest, like, I mean, I agree there are like limitations, and I like that there are maybe inherent problems with learning of word models and so. But I'm bullish not on LLM like in sense of LLMs, but I'm basically bullish that if I keep the LLM as it is, and I say that's good, I'm bullish on like with RL you can improve them. So maybe we should do it different way. Maybe it's not LLM, but the fact that you need at the end of the day like that something that needs to like explore and improve itself. I don't think this is something that will go away, even though if you change like the training scheme or use the architecture for some like. So I think that's more of the longer discussion, I would say, like LLM versus. So I'm like take it as X, it can be LLM or Jan LeCun's architecture, and then, but I bullish that you would need this kind of self-generation and self-play to improve. So, but we can talk about it maybe, about the other part of LLM maybe after the talk.
Hi.
Yeah.
So I just wanted to ask, one of the only times I really used reinforcement learning, I implemented DDQN to play Super Mario. Yeah.
Yeah.
And after a lot of fine-tuning, the model, and I mean parameter tuning and stuff like that, the model was able to beat the first level. Then moving on to the second level, I realized that my model hadn't really learned how to play Super Mario like I would have, but it just learned the correct combination of inputs to beat the first level. And in the second level, the background is different, the enemies have slightly different colors, and the model was completely starting from scratch. So what do you think in general is the main idea behind making sure that a model is actually learning the core, let's say the low frequency elements of an environment, the core elements of an environment, and it's not stuck on the high frequency? So let's say they keep consistent elements.
Yeah, so I guess so you did fine tuning. So this is basic example of overfitting, and I mean it could be technical issues. For example, I would on more a more diverse data has better embeddings, so has less probability to collapse.
You can do also some technical things, for example, like, I don't know, like freeze the layers here and there, or maybe add some supervised data here and there. So I would say it's, again, like, this all really depends on there's a lot of moving parts in the example that you said. It might just be that the setup is not like perfect that you are training, like maybe your data is like too narrow, let's say, maybe your pre-trained model is not very good. So it's difficult to say but there are things you can change. And how, to the second answer, like a more general answer, that how these models can be better, like, I personally think is really, like, many of this lies on the pre-training, you know, like, basically most of this learning a good embedding, which is the key of generalization, is all, I think, lies in pre-training. Like, the better the pre-training is, the better, the easier it would be to post-train, fine-tune them to generalize to different tasks. Of course, on the post-train, there's other tricks you can use, but I feel that most of it probably will come from better pre-training, like on top of some of the tricks that you're gonna use, like to make sure like the model doesn't collapse and stuff. But yeah, okay. Okay, maybe, okay, we have only 15 minutes. I just quickly go, so I just wanted to go, I mean, anyways, you probably know, I just go quickly through some of the like RL foundations. Most of it come from, if you haven't read this book, just read it, everything's here. The reason that I didn't put a lot of time on this, because I feel that there's so much material out there that is not for me needed to come and repeat. I just wanted to excite you about RL, that was the reason. But I can go for 10, 15 minutes just, you know, about some of the fundamental concepts. So if you want to now like put the big picture, like this is basically how all this system works. You have some agents, you have some environment, and agent takes some action, and that action will change the state of the environment, or and then environment will give you a feedback that what is the current state, which we call the observations of the environment. On top of that, you will get a reward for the action that you took. Now, basically the agent goal is to take the action that will maximize the total reward it collects like over time. So basically, this is it. And what is environment? Environment, like again, we talk about it. Like environment can be Atari, can be AI system, like LLMs, like can be chess, Go, robotics. So that's environment. That's where agent lives, basically, right? That's the world of the agent. And basically, the relationship between environment and agent is follows. Agent picks an action and sends it to the environment. As a result of this action, the state of the environment might change, and environment communicate that via like giving some observation. And basically what agent does, agent map the observations to actions, so which we call it policy, with the goal of optimizing the reward. So where the reward come from? This is a very important question. It's still, like, I think this is one of the main questions in RL that should be answered. So you can put like reward generation in two different categories. One is called extrinsic. So this comes from the environment. So this is the one that, for example, the score you get in Atari, or the reward you get, you know, when the robot's going, the speed of the robot is running. These are the hard-coded by the environment designer that we call reward. And these are usually like, you know, these are the ones that can be hacked if you don't design it very well, you know. There is other class of rewards, we call them intrinsic. And these intrinsic rewards are actually very interesting because they are generated by the agent itself. It's not given to you by the environment, but you can actually design your agent, like in your algorithm, that it will, on top of like optimizing for the extrinsic reward that comes from the environment, it's optimized for another reward that would help it to optimize the extrinsic reward, which usually it makes the agent to be more curious, find like more novelty, look at the learning process. I think this second one, even in the LLM space, needs more research. Like that, for example, if you don't have a verifiable environment, like how you can make the agent to learn like a better like generations. I think the second. But for this lecture, we will just focus on the extrinsic part. But I just wanted to mention it. Okay. So now it is the first piece of formalism that we have. So to reason about RL mathematically, we frame it as a Markov decision process, or MDP. And this is just a formal way of describing the agent environment loop. So the same thing that you saw, like the agent environment loop, you can describe it now in this mathematical framework. So we can now start to reason about it in a mathematical way. So what is MDP? So MDP basically consists of 5 parts: a set of states, a set of actions, a transition function that tells us what is the probability of moving to a new state given our current state and the action. So that's basically the transition. Sometimes you know it, sometimes you don't know it. And then reward function, of course, and the discount factor, which I will discuss in a moment. So basically, we got that picture of the environment agent loop, and we put it in this framework. We formalize it this way, okay? So let's make this a bit more concrete with a simple example. So let's assume that our world is a grid world, okay? That smiley face is the agent, like that's basically the empty places are reachable, and then you want to get to the goal. So you will have, like in this particular world, you will have the 4 unique states, right? So compared to Go, for example, that you had like more than the atoms in the universe, you have here 4 different states, right? And the one is like that when the smiley on the left corner, and then the second state, basically that's a smiley move. So you have all these 4 states, and then the terminal state, which is our goal, where we want our agent to be at, is the green one. So it's usually a start state. So this is what a state is, and that's what you define your MDP, that you say what is your state space. So action space is basically the ones that would change the state of the smiley. Like, so if you put right, it will go to the right, and then up, go up, down, and left. So this is just action space of our environment. And transition model is basically here are just deterministic. So basically, if you are on the top left square and you take the right action, you always end up to be on the right top of the square. And the rewards are defined by the goal. You just get the positive reward if you're reaching the goal, and negative if you get to the goal, you get a reward of 10. If you just go to the empty cell, you get a reward of 0, and then if you hit the wall, you get -5 for a small punishment. And you see, this is just heuristic. I designed it, so these rewards are just designed by the human designer or environment designer. And there is one more thing about Markov decision process is the Markov property, the assumption that we always make. And the assumption in the Markov property is that the future is independent of the past, given the present. In other words, to decide the best action to take right now, all you need is to know what is the current state. For example, like chess, the board position tells you everything you need to know. You don't need to know the path that how you took to that position. So this is the Markov decision process that basically you can make a decision just based on the current state you're at. And, and the agent goal mathematically is to maximize the discounted sum of future rewards. And now what is this discounted is? So basically, like, you want that agent start from here. When it takes one action, this action will eventually, even though it's a sequence of action, but that one action eventually take you to the sequence of actions that give you the highest return at the end. And what is the discount factor gamma here? So discount factor gamma here is a number between 0 and 1. It means that the rewards in the distant future are worth less than the rewards that we get right now. And this is for two reasons, basically, this discount factor. It is, first of all, it is mathematically convenient and ensures that this sum doesn't go to infinity, right? So if I didn't have this discount factor, this sum would go to infinity, and then everything will blow up. So that's one reason. The second reason is just you encourage the agent to be efficient and not procrastinate to achieve its goal. Okay, so it's just to get to the goal as fast as possible, because the more it delays reaching to the goal, the more the reward will be discounted. So you kind of make that's why I say, like, Q-learning, for example, like, inherently would encourage you with this discount factor to find the shortest path to the goal. And then you have the basically policy that map the states to the action. So the optimal policy is the one that maximizes the discounted sum of the future rewards. And then what is the state value function? So this is basically the most important concept of reinforcement learning. Like, I mean, that's the reason reinforcement learning is there, which is basically used for solving the credit assignment, right? So this value function would tell you that how much this state T would contribute to the future outcome. So basically, like, you give it the state and say, how good is to being this state for the future outcome. So this is the information it gives you. And even more useful than that, we have the state action value function. So other one was only on state, but this also will evaluate the actions that will tell you that in the current state you are, if you take the particular action and then you continue with whatever policy you have, what would be your future reward, basically. And this is the one that it's very simple. If you have that, if you know what is the value of a particular action in the future, then optimization is easy, right? So if I have 4 actions and I know what is the Q value for that 4 action, it's easy. I take the action with the highest Q value, right? So once you build this, then the optimization is very easy. And that's why it's the core of, I think, reinforcement learning that you want to get right. Okay, and there is this relationship between the value function and Q function, which basically value function is marginalizing the actions over the policy for the Q. So if you average out all the Q values for all the possible action for the state, you get the value function. Okay. So in summary, like I showed you what MDP is a world of the agent. Then it's policy. That's what our goal is to learn, and the value function is the one we use to optimize the policy. Okay, I think. We have 5 more minutes. If you have more to present, we can go over a little bit. Yeah, I think if I go to this one, then it needs to go another half an hour. So. Yeah, I think let's open up for questions, because I think, honestly, like, I like people have more intuitive understanding, because again, it's very difficult to go all the details. So I think all I want that you know that you learn this Q function that will tell you what is the value in the future, and then you optimize that Q function to get the actions with the highest Q value. It's really like what you want to get out of it. And then the details, like, I think you can get later. But yeah, I open it for questions. We have 5 minutes, so if you have any question, I'm happy to answer.
Hello. So my question is about what are your thoughts, like in which order we learn things? So what do you think about LLM reasoning systems and things like that? Is it important to kind of teach concepts in some way?
So my short answer, yeah, like curriculum it is important because if you start with the very hard problem, you will just kill the exploration. So it's just not going to learn anything. So it's natural. Is of the current ability of your agent. This is the core principle in optimization, that you always optimize everything based on your current ability, right? So like even when you learn a Q function, you don't learn a Q function for like what is that expert thing. You learn a Q function how good the current agent is, and then use that. And that's actually like I think good mathematical like framework for curriculum learning, that you don't want to like.
I understand that in the mathematical sense, that means that the R function is very easy to compute polynomially with polynomial complexity. This is the key characteristic of the so-called NP complexity.
You always have that challenge and that risk that you will learn something suboptimal. Now, how that improve it again? Like that's you know, you can start from some pre-trained model, you're close to some usually how you want to solve the basically local optimum problem, the current distribution of data, to make it to sample somewhere else, or make it like some teacher or someone else show it like another kind of sample.
i to je bilo u še...
Hello? Yeah, okay. I'm Razvan. Nice to, I don't think we've, yeah, nice to meet you. We will be starting soon, so please come in and find a seat. Can everybody please find a seat? Can everybody please find a seat? Okay. Okay, we'll start with our next lecture. So if everyone could be quiet, thank you. So we'll start with our next lecture. It's my great pleasure to introduce, and I'm going to butcher the name, but Milica Kasic, close enough. yeah, well, yeah, anyway. Milita is a professor at University of Heinrich Heine in Düsseldorf, and before that, she was a lecturer at Cambridge, where she also got her PhD, focusing a lot on NLP and dialogue, she's gonna be our first lecture on language modeling and conversational natural language modeling. And with that, let's give her a hand. And yeah.
So I will talk about natural language processing, but actually more conversational natural language processing. But before I dive into that, I have a puzzle for you. Does anyone know what this is? Good, yeah? Any other ideas? Sorry?
Oh, it's not. Oh, yeah, it's a song about the tribe of Azra. The beginning of it in German.
Well done. Where are you from, if I may ask?
Oh, Sarajevo.
Well done. Excellent. Okay. Well, for those of you who don't speak this language, what we've just done here a little bit was natural language processing. We have here some text written in some language, and a typical natural language processing task would be to ask for each word or phrase here what part of speech it belongs. So you can have adverbs, verbs, articles, adjectives, nouns, prepositions, and so on. You can also do named entity recognition, which is to find phrases which could be per people or time or location. So in this case, Sultan's Tochter is a person, Abendzeit is time, Springbrunnen is the location. But you can do much more than that. You can do question answering, which is just what I've done here, or sentiment analysis, find out about emotions expressed in this text. Or what I suspect most of you wanted to do immediately when you saw this is to translate it into a language that you speak. But we can also have dialogue about this and follow-up questions. So, until recently, the strategy in NLP was basically to have a conference on each of these topics. You can even have professorship on these methods that are devoted to study each of these tasks. But actually, nowadays, they are all addressed with a single kind of technology. And that is language modeling with deep learning. So I will borrow here Ferentz's start, and I will also start from y equals f of x. But what is x in the case of natural language processing? Well, that is the context, or the sequence of preceding words. And y is the next word. And what is f? Well, f is a differentiable function in theta, and the one which we like the most is transformer with a softmax output layer. And I won't have time today to go into transformers, but there is two things that you need to remember. First, that it is differentiable in theta, and that it can take a variable length input. So x can vary, but theta is always of the same size. So the number of parameters are independent on the length of the input. Sorry. All right, but one important thing is now to decide on these parts that constitute our vector x. And when you see this text, the first thing that comes to your mind probably is to segment it into words, right? But actually, there are many languages which don't have such clear segmentation, so you can work with characters or with letters. But what's most common with current large language models is to work with subword units. Okay, and then imagine somebody gave you this f of theta. How does the generation process works? How do you actually solve all these tasks with simply predicting the next word? Well, very simply, you use this property of the transformer that it can take a variable length input. So your first context, x0, is your prompt. Your y of 0, the next word, is f theta of that. Does this work? No? Okay. Of that context. And then to get the next context, you simply concatenate your previous context with your next word. And then you apply your f theta again to get next word, and so on until the end of the sequence. Okay, well, we actually use this softmax layer because we can interpret it as a categorical probability distribution, which is very nice in natural language processing, because in natural language processing we like variability. You don't always want to get the same answer from your, in case you're having on your chatbot or dialogue or in translation. So we actually sample our next tokens. All right, but how do we get this f of theta in the first place? Well, what people do is like this kind of quite a brute force approach. You take everything that's in digital form that you can get your hands on, and your objective is minimize the cross entropy loss. But what kind of function does that give us? What kind of language model does that give us? Well, that only yields the performance of an average internet user, and quite possibly not even that. So what can then be done? Well, then the next step is called supervised fine-tuning, where you get an expert to produce your pairs of prompts and adequate responses. So if I asked the question, what is this? An expert that we have there in the second row would say, Der Azra by Heinrich Heine. And then you can continue, oh sorry, it's a bit too quick. Then you can continue training. And you can get an improvement in your performance. And actually, there has been for a very long time an understanding in natural language processing that supervised learning will solve, is everything that we need, right? That you just need more expert data, better curated data, more data, and so on, and that you will then produce your language models. But that is actually not everything. as we heard this morning, there is a whole new, another area of machine learning, which is reinforcement learning. And as we heard this morning, in reinforcement learning, we have an agent that is interacting with its environment. It is in some state. It takes an action and receives a reward. And then we can define the return as a long-term reward. All of its rewards throughout the episode, if we talk about episodic learning, or lifetime, if we talk about lifetime learning. And then the goal of this agent is to maximize this reward, to choose actions in such way that this long-term return is maximal. Okay, so then you can have a policy. The aim of reinforcement learning actually is to find the right policy, which defines the distribution of our actions for a given state. And the goal is to find the best policy. And which is the best policy? Well, the one that generates most return. And if this policy is differentiable with respect to parameters theta, you can use policy gradient theorem to calculate the gradients. And one algorithm that you can use for this purpose is proximal policy optimization, or PPO, but there are very many others as well. Okay, so that's reinforcement learning, but how do we now apply reinforcement learning to our language modeling task? We need to define the state, the action, and the reward, right? Okay, so let's have a look. Well, context is the state, right? Our X is the state. Next token is an action. And our language model is the policy. But what is the reward? Where do these rewards come from? Okay, so now I'm gonna construct a reward model. And here I have an example of a preference data point. So the prompt is there a translation of Der Azra that an audience in Sarajevo might know of? So the question now is, which answer is better, Y or Y prime? Y prime? Yeah, everybody agrees on that? Yeah? Good. All right. So now we have these data points, and we want to construct the reward model. And this reward model will itself be actually a transformer or a language model. So it can take the pairs of X and Y, where X is the prompt and Y is the potential response. And R will be a numerical score for that pair. And this G of phi is a transformer language model with a sigmoid as the output layer. And the thing is, we can now fine-tune this reward model on the preference data. Okay, and that gives us the reward model G of phi. Okay, so how does then this fit together? Well, this then forms reinforcement learning from human feedback, which is also known as RLHF. So the first state is the prompt. The action is the next token. And now you need to decide on the reward. Well, if you have not reached the end of the sequence, reward will be 0. Otherwise, it will be given to you by the reward model. And the next state will be the concatenation of the current state and the action that it took. So now you have states, you have actions, you have rewards, and you can apply reinforcement learning to fine-tune or post-train your language model. All right, so for those of you who are not from NLP, I think this is, I suppose, the most important work that appeared in the last 5 years. It's the Instruct GPT, which is, but still, the results are quite impressive. So what do we have here? So on the y-axis, you have model size. This is the size of your theta, right? And it can go from 1.3 billion to 175 billion. So it's even difficult to imagine how large that is. And this blue line here is the performance of the model that just trained using this kind of the pre-training, so without any supervised fine-tuning. And what they're measuring is, here is the win rate against the best models that trained using supervised fine-tuning. So that's the green line here. And obviously, the more parameters you have, the better it becomes, and it can't really beat itself. So that's the maximum. That's where the 50% is, and everything below that is pretty much worse than chance. Okay, and then with this very tiny bit of data that they used for reinforcement learning, they have these two models up there, the PPO models, and they showed that even the smallest reinforcement learning trained model beats the largest supervised training model. And this just shows the potential of reinforcement learning and how important reinforcement learning is, even for tasks where it's not, I mean, entirely obvious that this is somewhere where we should use reinforcement learning in the first place. All right. So we actually used reinforcement learning in task-oriented dialogue for several decades already. And how is task-oriented dialogue different to chatbot or a large language model? Well, the crucial difference is that in task-oriented dialogue, we assume that the user has a goal that they want to achieve during this conversation. And that there is an external knowledge base which kind of contains human-readable external knowledge source, which is undisputable, and that the system needs to interact with this knowledge base in order to solve the goal of the user. But it's only communicating with the user in natural language. And therefore, this conversation needs to take place over several turns in order to fulfill that goal. And the system maintains an explicit estimate of user goal throughout the conversation, which is called the dialogue state, in order to have a goal-directed conversation. So just to give you a difference, when you ask LLM a question, LLM is trying to give you the best possible answer. But LLM is not trying to have a representation of your mind of why you're actually doing that. And it's not trying to to then have follow-up questions in such a way that it's predicting the outcome of this conversation. All right, so what do we need, what do these systems actually need to fulfill? Well, on the technical side, they first and foremost need to be accurate, right, in order to be usable. But closely related to the question of accuracy is the question of calibration. It should be convinced about what it is telling us. It should not tell us one thing, but actually not believe in that. It should be robust to noise, and it should be adaptable. In terms of the fact that they are interacting with the human, that means that they need to be human-like and personalizable. And in terms of ethics, they need to be explainable, unbiased, and private. And if you think about this ecosystem where these systems live, they need to be efficient, so use the resources responsibly, but also we want to have open source models to support, to foster future resource. So I will then structure the rest of my talk basically in this order. I will talk about something that we did in the open source front, and then I'll move to adaptation, achieving human-like performance, calibration, and then just a tiny bit of explainability at the end. All right, so in task-oriented dialogue, I already said there is this external knowledge base. Well, the scope of this knowledge base is actually described by ontology. So in this dialogue benchmark that we designed quite a few years now, there is an ontology that's described in terms of domains, slots, and values, and system actions and user intentions. So you can think of this as like symbols in neurosymbolic approach. Then each dialogue is labeled with the success and failure on the dialogue level. And we have annotations for dialogue states, system actions, and user intentions. So this was actually an effort led by my former PhD student, Pavel Budzianowski from the University of Cambridge. As I said, it's quite a few years now, but back then this was the largest task-oriented dialogue benchmark available, containing more than 10,000 dialogues spanning over 7 domains, and you can see that the number of turns is quite large, so it had almost on average 15 turns. And so the conversations are not real conversations, so they are collected in this Wizard of Oz style, where you have 2 users talking to each other, but one is pretending to be a machine. So they are like fulfilling the task of a tourist information call center. And yeah, so the domains that we have are restaurants, hotels, attractions in Cambridge. And the goal is finding multiple entities, making a booking, or scheduling a ride. So all of these things require this kind of multi-turn interaction. All right, so then with my group in Düsseldorf, in particular my PhD student, Shutong Feng, we actually extended this benchmark to include emotions. Because emotions are something that's really only studied in chit-chat dialogues, in social dialogues and so on, but we saw that emotions are an integral part of any kind of communication, including this kind of transactional communication. So we then labeled the data set with user emotion, and here are the classes, and also system conduct. We call them conduct rather than emotion to avoid anthropomorphization here. And you will see later how we use this. All right. Another effort, which was together with Tsinghua University and Microsoft Research Redmond, was to produce a toolkit for building these task-oriented dialogue systems for different kind of corpora, including multi-WOS. And there we have a user simulator. I mean, you heard this morning how important simulations are if you use reinforcement learning. Well, this toolkit allows us to do that. We have dialogue state tracker, dialogue policy, and natural language generator. I'll talk more about this as we go. Okay, now I'll get to the first point, which is an adaptable conversational agent. Often the problem is you develop some system, you collect data, and then something changes. Like you get new partner, somebody adds some restaurants or a whole new domain, and then does that mean you need to start from scratch? Well, adaptable conversational agent will learn continually if it does not forget old tasks, if it can apply to new tasks what it learned on previous tasks, and if its capacity does not change. So, as you can imagine, we used transformer encoder decoder architecture here to describe our policy, where the encoder encodes the dialogue state, the decoder generates dialogue action, and the objective is this long-term dialogue success, which I will say a little bit more now. So the transformer already has a lot of its inherent abilities to support continual learning. We achieve forward transfer by encoding domain slots, values, and system actions and user intentions in natural language. And this transformer prevents forgetting by operating with a discrete but unbounded number of domain slots, values, system actions, and user intentions. And its capacity is fixed. So this was developed by my former PhD student, Christian Geishauser, and he named it Dynamic Dialogue Policy Transformer. So we also have this simulated environment that was developed by my postdoc, Xinjin Lin, and this environment allows us to have domains that occur again, so multi-domain dialogues and user demands that changes and multiple users. So here I'm just going to give you an example. I don't know whether you can see actually, or is it too small. So you have here on top user goal. So this is something that's only known to the user simulator. And based on this, user simulator takes an action. And now what a dialogue system is doing, it's trying to figure out what is the current user goal, what was the current user action, takes into account the history and also the database results. So what do we actually have in this external knowledge base? And that whole thing forms the dialogue state, based on which it produces system action in this symbolic language. And then we get some reward. So if the dialogue is finished, we check whether it's successful based on the user goal. If it's not if it's successful, it gets large reward. If it's not successful, it gets very small reward. And if the dialogue has not finished at all, it just gets a very small reward to a negative reward to incentivize more efficient processing. Okay, but here comes the important part. What kind of rewards are useful? Or more specifically, what kind of returns are useful when we think about an agent that's learning continually? So that's during its operation, it's interacting with different kinds of users, the databases that it's operating over are changing. What is the adequate reward for continual learning? So what is somehow like the simplest approach is to say, well, I'll just use the episodic return, right? The aim is to have a successful dialogue. So I will check at the end of the dialogue whether this dialogue is successful or not, a bit like playing a game of chess or Go, and then try to learn from that signal. But what Chris did here, he introduced another kind of objective, which is called lifetime return. So he was looking at what is actually happening during the whole lifetime of this agent. How much total return is this agent obtaining? And then what he used is the CLEAR algorithm. It's a reinforcement learning algorithm that has two competing objectives, maximizing the entropy of possible actions, so allowing exploration. What we heard this morning is there is this dilemma between exploring the space and exploiting, and regularizing towards past behavior. So this is effectively a kind of exploitation. And what Chris did on top of it, he introduced meta-learning to let the agent on its own learn when to maximize the entropy versus when to regularize over past behavior. Okay, so we have now several things going on. We have our episodic return, we have lifetime return, and we have meta-learning. And here are some results. So here on the x-axis, you see the number of training dialogues. But actually, and then on these at some points in this lifetime of the agent, some things change. Either you introduce a new domain, or the user demand changes. So it's not a fixed environment, it's a stochastic environment. And here we measure the success rate. And you can see that on the bottom one, the blue line is just the learning using episodic return. And then if you do instead the lifetime return, you already are doing better. But the green one is episodic and lifetime. But actually, when you do meta-learning on top of that, that gives you really the best performance. Okay. And here we looked at differences between PPO and CLEAR. And we looked at single rule-based user or deep learning-based user, that's TOS, or multiple user behaviors. So sometimes you can have more difficult one, sometimes easier. And actually, you don't need to understand all of this, but what's really interesting is to look at the last column, which is the most challenging one. You can see how that PPO gets pretty much always negative lifetime returns. Whereas with CLEAR algorithm, we can really improve massively by starting from episodic learning, which is just the blue box there, all the way to adding meta lifetime learning on the top of it, which then really improves the performance. Okay, so takeaway message, think about meta learning. It's really, really important. Okay, The next topic is human-like interaction, and we can't talk about human-like interaction without talking about emotion. And this dynamic dialogue policy transformer is very nice because it can actually include, you can very easily extend the state space. Remember, transformer allows you to take any kind of input. And in terms of generation, you can just keep generating, so you can change the generation space. And now comes the question of the reward. How is reward related to emotion? Well, if you're building a conversational system, probably would like to elicit positive sentiment in the user. And you can use that as the reward signal in your reinforcement learning framework. Okay, so here we compared an LLM fine-tuned with on this EEML data in a supervised fashion. And I won't go into too many details here. It operates on delexicalized output. So this is a bit of a hack that people use because it's difficult to produce like nice text. So you put placeholders on things which you can directly take from the database. So for example, in the database, you have some value column for a particular slot. Like if the slot is area, then area could be north, south, east, or west, or could be a particular part of the city. And then you just take that as a placeholder, and then using some rules you fill out before you present it to the user, just fill it in. But as you will see, that actually produces a lot of errors. And then we have this modular system where things are actually divided into understanding, policy generation. But what's important in terms of reinforcement learning, it has two kinds of objectives. One is dialogue success, dialogue level objective, and the sentiment of the user, which you can actually estimate on every turn. Okay. So we tested this on the user simulator. And here are two llama models. One simple llama without emotion, EEML llama with emotion. And as you can probably imagine, that adding emotion is good. On the user simulator, the sentiment improves. But what's more important is when we test this with real humans, then we see that both success and sentiment are bad. And then we have this, but here with LLMs, we couldn't quite get to check these kind of effects of reinforcement learning, which we can easily do in modular systems. So here we have the simple loop method, which does not have emotions, an EEML loop, which has emotion on the turn level, and dialogue success on the dialogue level. And what we found was that, oh, sorry, this is 91 here, not 9%. This is 91, there was a typo here. That both success and sentiment improves. But the thing is, this modular approach is not very elegant because there is a lot of information loss going on between modules. And this is very nice in LLMs because you just have one network doing everything for you. And then we were thinking, well, could we get the best of both worlds? I mean, get ideas from modular systems about using these rewards that allow us to do different kinds of RL, but still utilize the beauty of LLMs where you have just one single network. So there is, then we tested this again. We took our emotional models and we measured the error that they produce. And you can think of this as a hallucination error. So how different is what they actually produce in the end and present to the user from what they intended to do, because we have this these symbols in between on which they operate. And here are the error rates at the last column. And then we looked at a more kind of brute force approach, which is just train a chit-chat model. And actually, in terms of sentiment, that model is quite good. But in terms of success, it's very poor. And we can't possibly estimate the hallucination error. We suspect it's very high. And then something which has been very popular in the last year is this agentic approach. I don't know whether you heard of basically agentic approaches. It's kind of more sophisticated prompting. You tell system what you actually expect from it to do. You allow it to perform some API calls to access external knowledge source. So this is what we did, and actually that system is better than a chit-chat system in terms of success, but not so good on sentiment. And then here, Xu Tongfeng proposed two solutions, which is to actually train an LLM with an external knowledge base and allow it to operate on fully lexicalized outputs and use reinforcement learning on turn level for emotion. So that's the first line here. And on a dialogue level with dialogue success. And you can see that that kind of model produces very high success rates, and it halves the hallucination error there, and has a competitive sentiment. All right. There was a... people usually talk about accuracy, but they don't talk so much about calibration, which is how much confidence the model is assigning to the response that it is providing you with. So we say that system is well calibrated when its confidence is aligned with its accuracy. So the system, if it's 70% successful on average, it should not put more than 70% confidence in its output. Okay, and there was, so this morning, there was this question of intrinsic rewards. So we think usually of rewards that come from the environment as a reward or punishment. But actually, in human learning, there have been observed a lot of these kind of intrinsically motivated rewards, like curiosity, for example. Another example from human learning is that we, in the absence of external rewards, often learn based on our confidences. And then we asked ourselves, well, can't we modify LLMs to do the same? So what we propose here is reinforcement learning from self-feedback. And how does it work? So we applied this primarily to reasoning tasks, where the system needs to do some reasoning and then come up with the answer. So when the system finishes the generation, we force it to generate so the answer is, and it basically then repeats its answer. Then you can find this answer span in the originally generated output and calculate some kind of confidences. In our case, we use disparity measure. And then you can use that directly as the reward signal. So it's a very, very simple idea. And how does it work? Where here is the performance on common sense QA with the Phi2 model. So you can do this on any kind of LLM. In this case, we took some small ones that are manageable to run experiments with. So here is, if you just use this model and greedy decoding, accuracy you get like 54%, and the expected calibration measure is 25. So this is how much expected calibration error. So how far away its accuracy is from its calibration. And then when we use RLSF on top of that, accuracy improves, but more importantly, the expected calibration error goes down. So here is an example. So from this data set, so the question is you have to do a lot of thinking while studying a new subject, but what do you gain from it? And then select one of the following: fatigue, depression, best way, weight, and knowledge. Probably can get all of that, but the model is kind of forced to choose one answer, but it can assign probability to it. And if you look at what kind of things these models do, well, they actually tend to put all of the probability mass on the selected answer. And obviously then when that answer is not correct, then that's a badly calibrated model. So here the model chose A with probability 99, while the golden answer was E with, and the probability it assigned to it was very, very small. Well, after we applied RLSF, which is a completely unsupervised method, actually we still got A as the answer, but the probability was actually lower. And it did assign some probability mass to the golden answer. Actually, what's really nice about RLSF is that it is a method for distilling a reward model from an LLM. So you can just take any LLM and set of prompts that you're interested in, and RLSF will give you the reward model for these prompts for that model. So we tested this on a reward benchmark, and these are the top performing reward models on that benchmark. AFD is alignment from demonstrations. So this uses ideas from inverse reinforcement learning to extract the reward model if you don't have preference data. So these best performing ones use preference data there. The AFD uses golden responses. Our RLSF uses neither responses nor preference data. Obviously, it's not as good as these other approaches because of that, but it still performs remarkably well considering that. And in the case of, was it in the case of Quen? No, in the case of Gemma, it outperforms AFD. All right, this is the final bit that I want to tell you, but it's something that we did very recently. And so this is nothing to do with reinforcement learning, but I want to talk a little bit about diagnostic measures we have about our f of theta. So our f of theta, as you know, can overfit, but it can also stop improving. And you at some point have to stop training. And somehow how you decide when you stop training is a bit arbitrary. But it can also grok. Does anyone know here what is grokking? Do you want to say what it is? Yeah?
You keep training the model even after this convergence.
Yes, and what happens?
Interesting.
Maybe you can add?
There is a weird behavior when apparently after lots of time training, even then training loss stops improving, you have an incredible spike of accuracy after like it was not performing perfectly, and then there is a spike of accuracy. I know that the reason why that happens might be because there is a exploration in a lost surface, and all like the optimal.
Okay, but where does the accuracy happen?
Like late
on
in the
which
training.
on which part of the data set? Where does this spike happen?
On validation data?
On validation or test data, yes.
Yeah.
So
obviously, yeah, not training data. Because,
yes, so on training data, you basically reached the lowest possible loss. But if you continue training, at some point, you will start, the loss will start decreasing, or the accuracy will start increasing on the validation or test set. So, and this shows that really it is important to know when to stop training. But as far as I know, there are no methods which can tell you just using trainings data when to stop, because everything looks the same, right? Loss is 0, so what do you do? Well, what we used is topological data analysis, and I will just show you very, very briefly how we did that. So this f of theta is a transformer with a softmax output. And these lower level layers of the transformer represent contextual embeddings of tokens. And let's now look at the penultimate layer and its embeddings ET for a token T in context. So what can we say if we took now all of these E of T's about this space? Well, some people would say that this space forms a manifold. And that means that you can locally, say around one token, measure the dimension of this space. And we can do that with the help of topological data analysis. So here I have some context. Anyone from Croatia here? You want to read it out? Okay, I will do it. Zagrebačka grupa Azra je dobila ime po pesmi Azra. Okay? So there are two Azras here, but these are contextually embedded. So they are in different parts of the space on this manifold. Okay? And now let's say I'm interested in this Azra here. I can zoom in to the manifold here, and I can measure the dimensionality of this subspace. And I can do this for every token that I see, and I can do this during the process of training. So what do I need? I need the model, and I need the training data. And then I get basically for every step of optimization, I get a number, a local dimension estimate. Now the question for you is, if I have these three phenomena, overfitting, just nothing's happening, or grokking, what do you expect this dimension to behave like? Any ideas? Do I see a yes, please? Shrink for dimension is a number, right? So it can increase or decrease or stay the same. Decrease for what? When? For which of these three phenomena? Sorry? Somebody said something, I don't know who. For grokking, it's going to decrease. Does anybody disagree? Yes? You think for grokking it's going to decrease? Okay. How many of you agree with that? Okay, 1, 2, 3, 4. Okay, for grokking it's going to decrease. Who thinks for grokking it's going to, sorry, you said for grokking it's going to increase. Who thinks that for grokking it's going to decrease? 1, 2, 3. Okay. Who thinks it's going to stay the same? Who wants to go for lunch? Okay, good. So, and the answer is that if the model is not improving anymore, it's going to stay the same. If the model is overfitting, it's going to increase. And if the model is grokking, it's going to decrease. And this is my final result that I want to show you. So here you have training steps on the x-axis. Okay, and here is the training accuracy. So this is just using training set. I'm not looking at test sets at this point. And this is the validation accuracy. So this is on the validation set. And you can see that at different points of time it's grokking. Every time these lines go up to 1, it means that it grokked. But for different processes, it happens at different points. But for all of them, more or less, the accuracy on the training set is already saturated, right? And this is the local dimension on the training set. And if you see here, green line, it's starting decreasing quite late, which means that the grokking is happening quite late. Violet line decreased much earlier, and indeed, that process grokked much earlier. Yeah? Is that clear to everyone? Yeah, okay, you can go for lunch then. Yeah. All right. Yeah?
Do you have some intuition on what happens when the grokking happens? Why the intrinsic dimension decreases?
Well, imagine being born and you are surrounded, like all of a sudden you're receiving so many signals from your environment. Like your input dimension is just huge. And then after a while, you start making sense of things. Things start repeating. You start realizing what's important, what's not important. Your dimension goes down. The dimension of your data pass through your model. When the model overfits, it's using more power to explain something which it can explain with much less power. So it's doing something strange. Yeah? Yeah?
Hey, thank you for the nice talk. I wanted to go back to RLSF. I think it's reinforcement learning with self-feedback.
Yes.
So we know that like language models hallucinate, like even with first-degree information, right? They don't necessarily know what to say. They say random things sometimes. And with RLSF, we're basically like looking at even higher degrees of information because we're like challenging model. What do they say about like different probability distributions? We already know like entropy estimation is a very hard problem, right? And it seems like it's such a granular information you're relying on to like model to train itself.
Well, I mean, I know that there is this concern, but actually all that RLSF is doing, it's moving the focus. Instead of just doing next word prediction and treating every token in exactly the same way, like whether it's a content token containing the answer or just like an article, it's exactly the same. And what RLSF is doing, it's saying, well, you should actually focus on the answer. Answer is what you want to achieve during the process of your reasoning. And you should just make sure that your answers, that you're confident in your answer span and not in the full stop that comes after it, you see? So it's just moving this probability mass to the part what is important. And then once you have something which can be characterized as a goal, then you can use reinforcement learning to achieve that goal. So we are currently performing experiments to check whether it produces more bias and so on. We don't think it will be, because it's not in any way better or worse than RLHF in that sense. It's just you tell it by saying this. So the answer is that this is where you would like the model to be most confident, and that's all what it is doing. Then, if that answers your question.
Thank you.
There's one at the back.
Thank you for the talk. If we can go back to the slide introducing the manifold analysis of the embedding space. No? Because in one of the slides you mentioned that you chose the penultimate layer
yes.
of the encoder. So my question is, it's probably because the richness of representation of the embeddings is already very high in this layer due to the depth. But did you do?
Yes, yes. We looked at other layers as well. I mean, this one is most informative. I mean, for this particular analysis that we did here with overfitting, grokking, and so on, this one is most informative in that sense. But you can do this on any layer you want, or you can do on all of them an average, and that's possible as well.
And those patterns are still present there, yeah?
Sorry?
Those patterns are still present in those previous layers, yes?
Yeah, I would need to check what is present. I can't remember. I mean, I don't remember it was so clear cut like here. I really think that for this purpose, you should look at the penultimate layer. And I need to check. I mean, the paper is on archive, so you can have a look. But yeah, I think for this particular analysis, the penultimate layer is most informative, yeah.
Okay, thank you very much.
Hi, so my question is, if this phenomenon holds, and do you think it would be useful and feasible to use this dimension as signal for a regularization during training or speeding up the convergence of the model?
Well, what I didn't say is that this is quite costly to do. So this thing here is not entirely cheap. So you have to be careful, like how you use it and when you use it. This is my suspicion is that, I mean, if you are, that you could somehow, the fact, so I think it's quadratic. And I think you can utilize the fact that the transformer on its own needs to look at context to maybe do some of these calculations during the time of the computation of attention, for example. That would probably speed up. But the problem is that you actually want here the closest neighbors rather than just anything from the context. So I'm not quite sure, but I definitely think that for diagnostic purposes it can be used. Whether it can be used in training, I think one would need to think a way of making it more efficient, or using the inefficient parts for like that. I mean, already we have to put resources in to calculate some of the things up front, so that you can actually, to make this feasible.
Hi. So my question has to do with the kind of the fact that I think that loss functions are heterogeneous, because we're trying to optimize over multiple different types of things at once: the embedding vectors, the attention waves, the multi-layer perceptrons, and then each block actually has different characteristics. And I'm just wondering, if we look at a very basic loss function, which is kind of like a parabolic bowl but has ellipsoidal contours, we know we're going to converge very quickly in the narrow direction because the gradient is big there. And then once we get kind of like to the center line, then only then will we go in the orthogonal direction, and that may be much slower. I'm just wondering whether the fact that it's a very heterogeneous loss function, we don't end up getting dimensions which will converge quickly to a low number, and then other dimensions were much more shallow. And maybe that's what explains grokking. I'm just wondering what your view is on that.
Well, I don't have a direct answer to this. What I could say, for example, so here we used TDA on the embeddings. But one other thing that you can do is use TDA on the parameters of your model, on theta. And maybe that would be more appropriate for your question, because maybe then you could, by seeing the dimension change of your parameters, or maybe not. I mean, there are other things you can measure, like the manifold of your. You can look at the manifold of your parameter space and characterize it. Maybe that would be more going along the direction that you said. But yeah, that's the best I could think of it right now.
Thank you so much. Very interesting results indeed. My question has to do with two aspects of this method. The first one has to do with the contrast between the episodic and the lifetime memory.
Okay.
It is if you have considered, instead of going over to the whole lifetime beyond T, to consider a framework of bounded rationality. We mentioned it
of what
as well.
Of what?
Of bounded rationality, like approximating G beyond T by the, let's say, the steady steady state distribution in the Markov model, instead of taking into account the whole future, and see if we have an.
But isn't that what this is doing? I mean, this is the end of the episode, and this is the whole lifetime. I mean, that's what it's doing. It's like looking in future beyond this dialogue. So basically, this agent has the opportunity to do something to achieve this particular dialogue to be successful, but it has also the opportunity to learn something. Maybe it might not be successful or on this dialogue, but it can use that as an opportunity, as a learning opportunity for all dialogues that are coming after. And that's the difference between
you might be using already this approximation. I see.
Yeah.
I see. And the quick second question has to do with the geometry. Since you are computing the localized geometry, have you tried examining the curvature of the space, like the Ricci tensor? Because usually this quantity is much more informative.
I lost it now. So,
for example, I would expect a negative curvature to lead to grokking as
So
well.
what we tried to do in another, I'm trying to find it now. What we tried to do is, let me just get it here. So here we just estimated dimension, but this is a manifold. And I mean, what mathematicians particularly like to do is measure holes. Now I don't really have a good intuition of what a number of holes on a large language model manifold could possibly mean. One thing that we had a successful application of that is polysemous words. Do everybody know what a polysemous word is? So like mole can be an animal, it can be something on your skin, but it can also be a spy, right? So this is an example of a polysemous word. So if you have a static word embedding, so if you imagine that this other here has exactly the same word embedding, regardless of the context, the space of these word embeddings can't possibly be a manifold because you will have singularities in the points which are polysemous. So what we did for that kind of, in that kind of case, we worked with punctured manifolds. And that actually then allowed us to have very, very simple way of achieving basically state-of-the-art results for noticing polysemous words. So that's one thing I could think of where these holes could make sense. But in a general, like a large language model like this, I'm struggling to get this kind of intuition. But I do think it's an important area for research because, I mean, it's a black box model and we need methods to understand it. And you will hear today in the afternoon about mechanistic interpretability. That's something else. This is just one other way you can actually think about these models.
Cool. We'll stop here because we're already late. So let's thank our speaker again. And yeah, she's going to be around for the day, so if you still have questions, you can just directly go and talk to her. Thank you.
Thank you.
Hey everyone, please take your seats. We'll start in like 10 seconds. Okay, hello everyone, welcome back. It's my very great pleasure to introduce our next speaker, Beyza Ermiş, who is a research scientist at Cohere. Beyza did her PhD at the Bogazici University, and she will talk today about AI safety and fairness, which are really important topics for everyone. And she is just sharing actually that she has some Bosnian roots, so we are really happy to have her here. So give her a big welcome. Thank you.
So I'm very happy to be here, and this is muted. Okay, perfect. So do you hear me well? Yeah, perfect. Yeah, in the last 2-3 years, I've been working on AI safety, multilinguality, and model evaluations, and today's talk will be the combination of all these topics. First, I will give a high-level view of what we mean by AI safety and why model performance alone is not a sufficient indicator of good models. Second, we will look at safety across languages, why harm is not universal, and why multilingual systems introduce unique challenges that current approaches often miss. And finally, we will turn to evaluation. I will talk about the limitations of current benchmarks and share ideas for building more fair and effective evaluation frameworks. To begin, I want to step back and frame what we actually mean by AI safety and why it's not just about performance metrics or benchmarks. AI safety is the discipline of ensuring AI systems behave reliably and without causing harm, even under stress or misuse. It's about practical questions like how to ensure the model doesn't hallucinate under stress, how to prevent it from being jailbroken into unsafe behavior, how to keep it from leaking private data or being misused at scale. One important distinction to make here is that AI safety is not the same as AI ethics. Ethics is about what values the AI should have, and safety is about making sure the AI-based models and systems behave reliably. So, AI safety is about ensuring reliable behavior, even under pressure or attack. But reliability can't be measured just by accuracy. That brings us to a key misconception, and one of the reasons AI safety has become its own field. Sometimes good performance is not good enough. In machine learning, we are very good at optimizing performance. We get good accuracy, blue scores, perplexity, win rates, etc. But safety lives outside the benchmark. Let me give you a concrete example. A language model gets 94% accuracy on MMLU, but it hallucinates a cancer treatment protocol 1 out of 20 completions. Another model passes a fairness audit, but leaks private data when prompted with a clever input. In these cases, the model isn't failing often, but when it fails, it does it dangerously. This is the distinction. Performance is about how often the model is correct. Safety is about what happens when it's wrong. And safety failures often don't show up in validation loss. They are rare, subtle, adversarial, or context-specific. So if we train only for performance, we are leaving high-risk blind spots open. That's why safety requires separate metrics, separate evaluation, and dedicated research. AI safety research is a set of interrelated challenges. Think of it as 5 pillars: robustness, alignment, privacy, misuse, resistance, and how we evaluate all of these. Robustness is about how well the model behaves when reality doesn't look like the training set. Can it handle adversarial inputs, unexpected tokens, noisy or real-world distributions? It's what keeps models from breaking the moment they hit production. Alignment is the most widely discussed and arguably the hardest. Does the model do what we want? Can it infer user intent correctly? Or will it refuse requests that are clearly harmful? And privacy is about the memorization. Large models can memorize part of their training data and they might leak them. This becomes a safety issue when personal or sensitive content can be extracted with the right prompt. Privacy issues hurt public trust in model deployments. That's why it's pretty important. Also, misuse resistance means even if a model is technically sound, it can be exploited. Attackers can jailbreak content filters, generate scams, deepfakes, or disinformation. And finally, since none of the above matters, if we can't measure it, we need safety benchmarks, tools, red teaming protocols, and uncertainty estimations. So together, these define safety as a multidimensional technical problem. AI safety is now a fast-growing research domain, technical, multidisciplinary, and well-funded. Major labs are publishing safety-specific work across robustness and alignment. On the institutional side, like UK AI Safety Institute and NIST are formalizing model evaluations and governance frameworks. And the research output has blasted, as shown in this DBLP chart there on the left. This chart shows number of papers from the academic conferences have fully embraced the field. And the chart on the right shows number of papers from last year's NeurIPS. Dedicated workshops are organized at top-tier conferences, and shared benchmarks and new tools for the teaming are emerging. Let's look at what has changed and why safety is unavoidable nowadays. This chart from Epoch AI shows the landscape of large-scale models from 2017 to 2024. Each dot is a major model, and they're color-coded by domain: language, vision, biology, speech, games, and more recently, multimodal systems. What's on the y-axis is the key: training compute in flops, a common proxy for model size and capability. You can see the shift. We are not just scaling up. These models now work across domains, and they're doing more than just predicting the text. Some reason, some plan, some take actions. As model gets more powerful, the risks scale too. A single failure can mean misinformation, leaked data, or unsafe decisions, and that impact isn't local anymore. As models become more capable and widely used, it gets more important to address safety issues systematically. This figure breaks down the mitigation strategies across the full life cycle of language models, from dataset construction to agent-level deployment. Let's walk through each stage. Before any training begins, we audit and filter the data to remove harmful content, sensitive information, or biased patterns. Whether it's for pre-training, fine-tuning, or alignment stages doesn't matter, we need this step. Then at the pre-training stage, we ensure that the training process itself is guided by safe and relevant content. This includes data filtering to exclude toxic, illegal, or biased content at scale, augmenting training corpora with curated or synthetic data that reinforces safe and relevant outputs. At post-training stage, alignment techniques like constitutional AI, RLHF, or preference modeling are heavily used. Safety recovery strategies, which are designed to mitigate or patch the vulnerabilities exposed during red teaming or deployment. For example, defenses against prompt injection, refusal tuning, or output filtering are also used at this stage. When models need to be corrected or adjusted after deployment, we rely on techniques from the editing or unlearning field. And some approaches are gradient-based model editing, memory level intervention, or locate and edit methods which trace unsafe outputs back to the data or architectural source and make targeted corrections. And the last part of this, section, I want to talk about the agent safety, which is the hot topic in AI safety research recently. As LLMs evolve into agents, new safety risks emerge. What are those? Tool attacks is one of them. Agents may be compromised through manual or gradient-based jailbreaks, tricked via prompt or tool injection, or manipulated by receiving biased or malicious content from external tools. To address these threats, we can wrap tools with strict safety controls, sanitize all inputs before execution, and verify outputs before they influence downstream behavior. There could be memory attacks. Agents with memory capabilities are vulnerable to long-term memory poisoning, where harmful data is stored and later recalled, as well as short-term memory erosion as well, where important context is gradually forgotten. Effective defenses include validating what gets stored in memory, detecting and monitoring retrievals for unsafe content, and modifying prompts or outputs to neutralize the risk. There could be environment safety. Agents operating in dynamic environments like games, the web, or media platforms can make flawed decisions or act unpredictably when reasoning or taking actions. Ensuring safety in such environments requires controlled perception pipelines and action limits or supervisory controls on autonomous decisions. And finally, the multi-agent risks. When multiple agents interact, they may carry out transmissive attacks by spreading unsafe behaviors, interfere with one another's reasoning or goals, or coordinate strategic attacks that amplify the harm. Mitigation strategies include adversarial red teaming between agents or consensus-based voting mechanism to detect these anomalies. So far, we have walked through the technical landscape of AI safety, but technical safety isn't the whole story. These models are deployed globally in different languages, cultures, and legal systems. And what's considered safe or harmful in one place might look very different in another. So we can turn to a critical but often overlooked dimension, scaling AI safety across languages. Let's start with definition of harm. Defining harm in AI systems is one of the most complex parts of safety work because harm isn't always objective. It varies across cultures, legal systems, or social norms. The same output can be interpreted very differently depending on who is reading it and where. Safety is also about respecting dignity, avoiding bias, and being careful not to erase minority perspectives. So the challenge is that not all harms are universal, but the model has to care all of them, and it has to adapt globally, culturally, and linguistically. Why safety must be global? Because there are over 7,000 languages spoken around the world. Roughly 400 of them have over 1 million speakers, and about 1,200 have at least 100,000 speakers. But at the long tail, more than 2,000 languages are spoken by fewer than 1,000 people. This matters for AI safety because the vast majority of these languages are reflected in training data, benchmarks, or red teaming. If a model is evaluated in just English or a few major languages, we are missing how it behaves in the rest of the world. Besides, the models are deployed globally and people interact with them in over 100 languages. Most of alignment research, red teaming, and evaluation still happens only in English, and that creates a gap. What is the current situation of AI safety? Is it currently global? So let's take a look at how the models actually perform across different languages. This chart shows the percentage of generations from GPT-4 that were relevant versus harmful. In high-resource languages, which is bottom of the chart, like Spanish, German, Chinese, the model performs extremely well. Almost no harmful generations, but in low-resource languages, which is on top of this chart, like Urdu, Maori, or Igbo, the model is far less reliable. Harmful completions can be as high as 30% or even more. Recent studies have also shown that jailbreaking attacks are more likely to succeed when prompts are written in low-resource languages. So poor multilingual safety doesn't just impact speaker of those languages, but it creates vulnerabilities that attackers can exploit across the board, like for also high-resource languages. But how much of this research is actually keeping up with the need? This figure shows how skewed our current safety research landscape is. It tracks all LLM safety publications from major ACL conferences and workshops over the past 5 years and highlights that an overwhelming focus on English-only work. Both English-only and multilingual safety research has grown over the time, but not equally. The growth is heavily concentrated in English-only publications. And this chart is really interesting to me because it shows how non-English languages are studied in LLM safety. On the x-axis, you can see that when a language is studied in paper, how many other languages are also studied with it. And y-axis shows how many times a language has been studied in these papers. For example, English, which is on the upper left part of the chart, rarely studied alongside other languages. So you can see that it's either 1 or 2 times, and the average is 1 point something. So it's mostly like deeply investigated. But the other languages are generally just investigated alongside with the other languages. Chinese, Arabic, and Hindi are mostly as part of large multilingual evaluations. And further out, languages like Nepali or Afrikaans only show up once or twice, often buried in papers that test 30 languages at once. That might look inclusive, but it's often very shallow. These languages aren't being deeply analyzed, they're just added for coverage. As we have seen in previous slides, one of the hardest challenges in multilingual safety research we face is the long tail problem. A small number of languages like English, Chinese, or Spanish dominate the data, the research, and the benchmarks. But beyond this layer, there's a long tail of hundreds or even thousands of other languages that are underrepresented. The other challenge is the alignment. AI systems serve people from different linguistic and cultural backgrounds. What's considered harmful in one context may be neutral or even preferable in another. You can see it better what I mean in this example. Here I want to show an example of global and local definitions of harm. The first one is an example of global harm and would most likely be classified as harmful by any model. But the second prompt, in Filipino originally, about indigenous communities may not be flagged as harmful by a generic safety system trained only on English data. These types of local harms require more nuanced and culturally informed alignment data sets and mitigation strategies. And the other challenge is the lack of data, especially for low resource languages and safety domain. Only around 14,000 languages are even candidates for NLP modeling out of over 7,000 spoken globally. That brings two limitations. One is training limitation. The model has little exposure to the language during any stage of training. And the evaluation limitation. Even if the model can generate content in these languages, we often have no benchmarks or annotated data to evaluate whether it's being helpful or harmful. And what are the solutions? Translation could be a solution, maybe. But most existing multilingual benchmarks are created by machine translating English datasets, including legal, historical, and toxic language tests. That causes a problem called translationese, where the translated text often lacks natural fluency, sound artificial or unnatural in the target language. And the second problem is the cultural bias. This analysis is from the global MMLU paper that I worked on this year. We have found out that 28% of all questions requiring culturally sensitive knowledge. And majority of this is Western-centric cultural knowledge. Translation, especially the machine translation, doesn't change that, and the underlying assumptions remain foreign. You can see some examples from the MMLU dataset here. The first question asks about the US Uniform Commercial Code. And the second one tests knowledge of the US Constitution. These are deeply US-specific references that don't carry the same relevance in other regions. Translating them into, let's say, Spanish or Bengali doesn't make them globally valid evaluation items. They still remain US-centric. And another example from a toxicity mitigation paper of ours. This analysis showed that how toxicity score drop when English toxic sentences are translated into other languages and then back into English. So we did this analysis to show that translation actually reduces the toxicity because these translation mechanisms don't actually translate the slurs, curses, etc. They actually make it more softened. So this is problematic for two reasons. If you use an English toxic data set to train models not to produce harmful content, and then translate that data set into other languages for multilingual coverage, it becomes less effective. The translations lose important signals, tone, slurs, or context, and the model may no longer learn to avoid them reliably. If you evaluate a model using translated toxic content and then translate the generations, it may appear safer because the toxicity is harder to detect for both models and for human annotators when it's translated. In other words, the model didn't actually get safer, but just look like that. That's why we decided to create an in-language data set, one that captures examples of both local and global harm written natively in each language. This data set is curated by professional compensated annotators who understand the cultural and linguistic context of their language. We asked annotators to write a harmful prompt in their language with their alphabet, select the categories of the harm, like local or global, and provide the English translation of these prompts without using Google Translate or its variants. Here you can see some examples from this dataset representing both global and local harm. As you may notice, maybe I should keep it for longer, local harm is often highly nuanced. It may not be immediately recognizable to someone who isn't familiar with the cultural, historical, or political context. That's exactly why relying on generic or translated benchmarks is not sufficient. Using these data sets, we applied several alignment techniques aimed at reducing harmful generations while preserving the model's general performance. To do this, we combined the in-language harm data that I just showed with general purpose alignment data sets, ensuring that the model learns both safety constraints and broad task capability. The general performance are measured on multilingual ArenaHeart and Alpaca eval datasets, and the safety performance is measured on held out set of the IRA teaming dataset. The results show that the model after alignment state generates much less harmful content, and the general performance also improves, suggesting that safety alignment doesn't have to come at the cost of capability. If you use the right, of course, if you use the right alignment technique. In our experiments, we also varied the type of safety examples, including in the training data, as only global, local, and global and local types of prompts. We found that training just on global data doesn't actually, isn't that successful using the local harm data on the local harm, so as expectedly, and vice versa. And the transfer from local to global is actually more effective than transfer from global to local. So we need local nuances. To sum up, in order to scale AI safety, harm evaluation and mitigation must be done across languages. Translated datasets must be complemented by human annotated or post-edited to incorporate local nuance. Extreme data scarcity must be addressed, and we should avoid content and knowledge bias in the test sets. I don't know if I should get some questions at this point before moving to the evaluation, or we can do it in the end altogether. Yeah. Or I can continue and we can take the questions in the end. Mm-hmm.
Thank you. I would like to make a question on the initial basis axis of the safety and security of the models. There is a similar list for software engineering. The CISA has made a particular initiative to get people to be involved with this, and as a matter of fact, Google is one of the signees. And I would like a comment if there is a parallelism and how do these two initiatives connect, the safety in machine learning and the safety in software engineering, because they share many close normalities in a sense.
So which figure?
The first one towards the start.
Oh, okay.
When we talk about robustness and
okay, yeah.
the basic features, the basic axis of.
Okay. So how related with the software engineering safety and the AI safety?
Yes.
I'm not so actually experienced in software engineering safety, unfortunately, but I believe they should be quite related. I can't see another aspect that might pop up in software engineering safety than the AI safety. Probably they should be aligning and on the same axis.
Mm-hmm.
Yeah.
I see. Thank you. Thank you so much.
Yeah, so maybe I can give more detail about this result. So this is the multilingual safety survey that we did very recently. Hopefully it will appear on EEML this year. So we were like group of 5 people, and we actually investigated all the papers by eye. So we checked all the languages explored in, like studied in one paper. And those are the languages which we have seen in those papers. We haven't even encountered any Eastern European language in any multilingual safety work. So the coverage of the languages is super small. There are a few groups in the world which is working on like Arabic languages or African languages. That's why there's like these African languages on very tail of the figure. And they just appear in like 3 papers or so in the last 5 years. But I haven't seen any Eastern European language study in AI safety, actually. The field is totally empty. So I will tell this in the end of the talk, but I can say it now as well. So if any of you are interested, we are very open to collaborate on this domain. And I would be happy to chat with anyone who is interested to collaborate with us. Yeah. So, other question? Yeah, if you're looking for some area to work on for your PhD or master, I think it's really like an area to work on because there's a lots of room for improvement and contribution. Okay. Mm-hmm. I think so, but I don't know if there are sufficient amount of supervisors who works on this type of research. I mean, there are very limited amount of people working on multilinguality in general because it's very difficult because there's no data, and when there's no data, no one wants to create the data because it's lots of work. I will also give some examples towards the end of the talk about like what we are doing. We have a community, by the way. Okay, I will advertise it later. But yeah, I think I would definitely do it because some areas are pretty crowded and it's hard to publish there. But this area is pretty fresh. There are lots of opportunities, and I think it's smart to work on this nowadays. So I would definitely suggest. Okay, up to this point, we have focused on the safety side of language models. But to build better models, we also need good evaluation. If we can't measure how models are doing, we can't make good decisions about architecture, alignment methods, or release readiness of the models. And there are also challenges in this domain. The main challenge is evaluation is fragmented. There are dozens of benchmarks. Many of them are task-specific, language-specific, or outdated. That's why the field has been shifting towards more scalable, robust methods of evaluation, especially those that reflect real-world user preferences. And one of the most influential efforts in this space right now is Chatbot Arena. Probably all of you know about the Chatbot Arena, which is a large-scale, blind, pairwise comparison platform that has become the de facto leaderboard for LLMs. May I ask how many of you tried Chatbot Arena? Do you still try, do you still enter prompts? It's a personal curiosity. I will come to that point, but I'm just curious about that. Okay. As Chatbot Arena has grown, it has done more than just provide a leaderboard. It has become a reference signal. Many traditional benchmarks are now being evaluated not just on internal consistency, but on how well they agree with Arena rankings. This agreement matters because it tells us whether our benchmarks are capturing something meaningful to users. So in a sense, Arena isn't just a leaderboard, it's become a kind of meta-evaluator. Today, Chatbot Arena has also become the industry's go-to leaderboard for evaluating AI capability. Obviously, Arena rank of a model matters because everyone is advertising their Arena ranking on Twitter when they release a new model. And why is that? Because with enough comparisons, Arena builds a stable performance ranking using the Bradley-Terry model, much like an ELO rating in chess. This approach has several advantages over traditional benchmarks. It's resistant to overfitting, adapts to new models, and reflects a broader definition of quality, not just task-specific metrics. What makes ARENA especially powerful is that it captures feedback at scale from real users on real prompts in real time. In a landscape full of statistic benchmark and shifting goals, this makes ARENA a unique, adaptive, and scalable tool for comparing models in the wild. So we said ARENA uses Bradley-Terry model, but what it is briefly. In the Bradley-Terry model, each language model is given a latent skill score, which we call lambda. The chance that model I beats model J is modeled by this simple probability formula, the first one. Over many matchups, the goal is to find the set of lambda values that best explain the outcomes we have seen. This is done by maximizing the likelihood function, which multiplies the win probabilities for each observed matchups, as given in the second formula. And once fitted, the result is reliable and interpretable ranking of models based on how often they win and against whom. While the Bradley-Terry model provides a principled framework for ranking models, it does rely on several key assumptions. First, it assumes unbiased sampling, that the comparison we collect are representative of true user preferences and not disproportionately drawn from easy prompts or biased matchups. Second, it relies on transitivity. If model A beats B and B beats C, we can infer that A likely beats C, even if they never directly face each other. And finally, the model assumes the comparison network is fully connected, meaning all models are either directly or indirectly linked through matchups. If a model is isolated, its ranking becomes unreliable. In the following part, we will explore what happens when these assumptions break down and how that can impact the reliability of rankings in Chatbot Arena. During our model submission this year, we explored that private testing is possible in Chatbot Arena. This figure shows that based on the scrap data between January and March this year, for example, Meta tested 27 models. And just a note, this was a bit before Llama 4 release. Private testing enables best of n strategy, and best of n strategy violate the Bradley-Terry unbiased sampling assumption. By using the Bradley-Terry model, we simulate a family of model variants with okay, it's back. So we simulate a family of model variants with a latent average ARENA score of 1200. As we progressively increase the number of private variants tested and subsequently get their corresponding ARENA scores, the probability of selecting models from the higher end of the performance distribution also rises. This enables the provider to effectively identify the model with the highest score. So the ARENA score can vary almost up to 100, which is quite high for ARENA. It might change a lot of rankings, I will show in a second. We also theoretically quantified the expected performance lift under realistic deployment conditions. In practice, model variants submitted for pre-release testing are not identical. They vary due to differences in initialization, random seeds, training data curation, or hyperparameter tuning, as we can expect. This inherent variability is captured by sigma true, which represent model level uncertainty. In addition, there's environmental noise introduced by the evaluation process itself, specifically by the number of diversity of prompts used during the testing. Because the models are not tested by the same prompts, right? So you just enter a random prompt and it's tested by that. So it should reach to a certain number of prompts to be representative. So this noise is represented by sigma noise, which decreases as the number of prompts increases. In other words, more prompts reduce measurement noise. If you know that sigma values, which are also inferable, you can compute the expected RNA score lift easily. And this another simulated experiment to show that impact of best of and submission strategies on arena leaderboard ranking. Model family A, and in this figure, model family A has a lower average arena score than model family B. But by submitting multiple private variants and selecting the best performing one, it can suppress the only public submission from model family B. This simulation shows how providers can gain leaderboard advantage by evaluating several variants privately and publishing only the top scoring one. And we also run a real-world experiment to measure the benefits of private testing. So we discovered that, and then we just wanted to try how our models will rank on the leaderboard. So we showed that it's possible to increase arena scores even in the most conservative case of identical checkpoints. On the figure, left figure, the left figure shows the identical checkpoints arena scores for IAVision 8B model. So we just submitted same model twice with different names. And that yield different arena scores and different rankings. It was quite different. And the right figure shows strategically selected checkpoints where arena scores for two different variants of the 30B version of this model. They were a little different. During the preference training time, we applied different strategies and we submitted these two. And for this one, the difference is even larger. So as we can see, best of N strategy really impacts the arena score. And the policy of the chatbot arena also causes the data access asymmetry. Chatbot arena is a community-driven leaderboard that benefits from free crowdsourced feedback and provided by everyday users. However, proprietary model providers collect significantly more test prompts and model battle outcomes than others. The reason is that Chatbot Arena only shares the data with you if your model is included in the battle. And they sample these models, which is more interesting models, that's what they said when we contacted to them. To keep the crowd more interested, they sample those models more. And Google and OpenAI have received an estimated 19 and 20% of all test prompts on the arena. And we estimate this based on the share of total battles played by the models of different providers on arena. And on the other hand, a combined 41 fully open source models have only received an estimated 9% of the total data. And then we also simulated what's the impact of this data which is collected by those companies. We run a simulated experiment with arena data. If you use more training data from a similar distribution, your model gets better on arena hard evaluation set, which is simulation of the arena prompts. So you can easily train your model on this data set to overfit to the arena distribution. And we also found out from the data that the models are deprecated in Chatbot Arena and are open weight and open source models more than the proprietary models. As I mentioned before, the Bradley-Terry model assumes a sufficiently connected comparison graph to produce consistent rankings. When models are deprecated unevenly, or when sampling strategies fail to ensure robust overlap in comparisons, the resulting history matrix can become fragmented. Through simulated experiments, we show that this can produce fragmented clusters, and as a result, the global rankings become unreliable. So the result on the right side of the slide shows that how are the rankings when the graph is dense and disconnected on the same data, and the rankings change drastically. And the final simulation about the Chatbot Arena is the rankings produced by the Bradley-Terry model are highly sensitive to the model deprecation, particularly when the prompt distribution changes over time. In scenario without deprecation, we observe the true rankings given that the Bradley-Terry model remains reliable. However, we observe the rankings differ if we deprecate model D between stages. While it's matchups with phase 1, the absence of updated comparisons causes a skew in the rankings of remaining models. Models A and D are ranked lower, and models B and C are ranked higher than the true performances. Maybe it's because the distribution changes. One model was better on another task, and we were seeing more math tasks in the beginning, and later it became more multilingual distribution, and it impacted the rankings, especially when that model is deprecated. Long story short, all these results show that the evaluations we rely on may say more about access than the actual capability. And when we ask which model is the best, it sounds like a straightforward question, but the deeper we look, the more we realize it's not just about performance numbers. It's about the quality of our evaluations, whether they are fair, transparent, representative, and robust. To evaluate models meaningfully, we need to ask the right questions, not just about how they perform, but under what conditions. Is it fair to compare models of vastly different sizes? Is it fair when they're trained on different data sets with different levels of supervision or filtering? What if one uses greedy decoding and the other uses temperature sampling or a custom system prompt? These differences can significantly affect outputs, and they're often hidden behind a single performance number. Beyond fairness, we also need transparency in how evaluations are conducted. Are the conditions of the comparison clearly stated? Do we know what data was used and whether there was any potential leakage from training? What tokenizers were used to score responses? And crucially, how was the model prompted? System prompts can dramatically change outcomes, but they're often under-documented. Without transparency in these decisions, even well-intentioned evaluations can't be trusted or reproduced. It is also important to know whether our evaluations actually reflect what users care about. Are they covering a wide range of tasks, not just benchmarks, but real-world usage? Do they include nuance and emerging capabilities like tool use or multi-turn reasoning? Or our evaluations stable under small changes? Do results hold up if we tweak the prompt, change the sampling, or run it on a different day? Can others replicate the outcomes? Robust evaluations are important for reliability too. Let's check some examples now. There are 3 multilingual models. The question is, how should we evaluate their multilinguality? In the reports, the models were evaluated on a number of multilingual benchmarks, but only a few benchmarks are generative. More importantly, only some generative benchmarks cover more than 10 languages, and the language coverage is obtained mostly by machine translation. So in this case, can we really decide which model is the best multilingual model? Another example is on reporting the results. Here we are looking at the same models evaluated on the same benchmarks, but sourced from 2 different technical reports. And the results don't match. This highlights just how much transparency in evaluation and reporting matters. Without clear documentation of the evaluation setup, it becomes difficult to trust or compare results across papers or releases. Also, it's important to know where the evaluation data comes from or how it's created. This example shows the evaluation results of the same model on different languages when different translators are used. This concludes that the translation quality matters. If possible, we should prefer target language original prompts. If not possible, we should measure, optimize, and document machine translation quality. And in most evaluations, we tend to focus on aggregated scores, one number that summarizes overall performance, but these aggregated results can be misleading because the way we aggregate can actually change how systems are ranked. So here are a few best practices I can recommend. Always report the full language or full task breakdown, not just the average. Validate whether averaging makes sense, especially across tasks or languages with very different distributions. And consider using meaningful aggregation groups like by language family or resource level. For example, you can maybe group the Eastern European languages together and the African languages together, but when you mix them all, I think you lose the nuance. Again, long story short, we need careful and systematic evaluation practices to build better systems. Finally, I would like to talk how can we expand the scope of evaluation. Existing evaluation sets are predominantly Western and English-centric. Vast regions of human knowledge and capability is unmapped. And under these conditions, how can we deploy AI globally? We can create more universal data sets. In the global MMLU work, professional annotators tagged each sample by using one of the cultural, regional, or dialect knowledge tags first. So we just hired some professional annotators who are expert in this domain, and they checked all the samples, and they just tagged those samples with one of those tags, cultural, regional, or dialect knowledge is required to answer that question or not. And then it's translated by the professional annotators in some languages, and our community translated this mid-group of languages. And unfortunately, some languages are only machine translated so far, but we have the system open so you can contribute human translating those languages as well. So that really helps the, more reliable, to make the evaluation more reliable. Because we first evaluated the models on the whole MMLU set. And then we evaluated it on culturally sensitive and culturally agnostic samples. So culturally agnostic samples are the ones who were, that were not tagged by any of these cultural, regional, or dialect tags. And the culturally sensitive ones have at least one of those tags. So when we evaluate these models on different subset of the MMLU, the ranking of the model performance changes a lot, especially on low resource languages. So the top two is the high resource, mid two is the mid resource, and the bottom is the low resource languages. And we observed up to like out of 14 models, you can see ranking changes up to 5 on the culturally sensitive data. So this is really important in the evaluation. And we also created a data set called Include that we collected the multilingual exams from 44 languages. Those are in-language exams, and again, the community members shared the exams from their country with us, and we cleaned that data set, and we created this Include data set. This is an alternative to the MMLU, which is more culturally representative, with more culturally representative samples. And Kaleidoscope is the multi-model version of the Include. So this is the multi-model exam questions. So if you want to test your model on a multi-model set, you can use this. It also covers 18 languages and 14 different subjects. And finally, we created IAVision Bench and Mild Vision data sets. We used the samples from these data sets, but we human translated them into 23 languages, and we tried to pick the most diverse and challenging images possible. It's also from different tasks like OCR, table, chart evaluations, and the visual QA answers. And to conclude, models are global. Our benchmarks and methods should be too. For this, we need new methodologies, data sets, better metrics, and more inclusive global collaborations for better evaluation of models. And I would be happy to chat with anyone who is interested to contribute to this effort. And thank you for listening.
Thank you for your talk. I wanted to ask, with all this problem in evaluation, what leaderboard would you advise to look at when comparing large language models now?
Very good question. I don't know, but I think more fair leaderboard is required, at least after seeing those flow in the current leaderboard. But I think it should be initiated by some people who really cares about the fairness of the evaluation. But right now, I don't have any recommendation for it. Yeah.
Thank you.
For most of the questions, actually, I don't have a clear answer. I think we should work towards this goal all together as a community. So that's the broad answer, but I hope I can answer more technical questions. Yeah, that's also very important. So, for example, this IRA teaming data set, we had 1,000 prompts per language, and there are 8 languages in this data set. Yeah. And there are 8 languages, 9 categories of the harm.
I saw a lot of authors in those dataset papers. So I'm just wondering, like, how the works are distributed and like how you manage such a big team to create such a big.
Yeah. So, for example, global MMLU took 6 months, and yeah, first we opened it for the annotation, cultural annotation, and then these culturally annotated samples are shared with the Cohere Labs community on Discord. I will share it in the Slack channel so you can join to this group if you want. And it took like 2 months or so for them to translate these samples. And then we check those translations, and yeah, we run those analysis on this annotated data. But mostly it takes a couple of months to create a data set, if not longer. So it's a huge effort, actually.
Thank you.
So maybe just to inform Beyza, this week we are encouraging participants to create teams and brainstorm on different topics, and come up with a plan and a pitch for by the end of the week. So I really think this is. I think we should count how many different languages do we speak all together here.
Yeah, that would be amazing.
I think it would be amazing to discuss a plan for such an evaluation. So yeah, if people are interested, maybe do ping Beyza or start a channel in Slack to discuss this.
Thank you for the talk. I had a question about fairness when it comes to training, for example, language models. So isn't there a risk where we're trying to be fair? We kind of introduce a bias, intentionally or not intentionally. Because, for example, there are some discussions for example, Google, for the early versions of models. There were some remarks, for example, where diversity were kind of was forced. Or sometimes there are some remarks regarding ChatGPT, since it's trying to there is some sort of political biases sometimes. So isn't there against fairness at the end of the day?
So you mean using those things is against fairness?
The intention is to be fair because there is the usual bias that is in the data, and in order to be fair, we try to balance that. So, for example, we're restricting what ChatGPT can say, but isn't there a risk of not being fair by doing that?
I don't think there's a risk of being unfair when you are trying to fix the unfairness, but I think it might hurt the accuracy, maybe. Because sometimes maybe that fairness should be there to perform better on the evaluation, because in the evaluation set, there's also like unfair opinions, let's say. So I think that might impact the accuracy more than the fairness, but I think we should keep forcing the models to be fair, or maybe do the post-training mitigation to like solve that type of issues.
I think maybe what I mean is that maybe fairness can be also relative, because I saw some papers come out that say, what do we really mean by fairness when it comes to this?
It's very actually subjective topic and a bit like multidisciplinary topic. I don't think computer scientists by their self can solve this. That's how I feel, at least. Because when I think about myself, I'm not so knowledgeable about the fairness, but I need help what's fair, what's unfair. So I think we need to collaborate with more like people from social sciences about that to decide on that type of things.
Hi, I have a question about how security checks are integrated into the training pipeline, because like if they are integrated into the training pipeline. So my question is this: it costs a lot of money and a lot of work to build a huge model. How do we work on fairness as the model being trained? Do we like check it at a certain point? How do we, can we spot the potential risks early? How we correct them as the model is trained? Or the safety measures that just like, you train the model and then you evaluated that and then you like create the blocks or something, or there is something along the training?
Yeah, it starts with the data curation anyways. So so I think you should be careful in every stage in it and what's done in practice mostly. So first you collect the data to train your model. And you check if the data is safe enough, but the data is so big and it's just crawled from internet, the whole pre-training corpus, and sometimes you can't filter everything. In the first place, mostly hard-coded filters are used, but you can't do a nuanced filtering. And you train your model, and after that you check on some like safety evaluation sets, like how your model behaves, and then you can do these alignment approaches to align your model with the human values, let's say, or more safe. So yeah, I think it should indeed be detected in early stages, but it's not so possible in practice. So yeah, you do it in every stage. And even you should do this machine unlearning at some point, because if it's somehow in your training data, you can't avoid it, and you need to erase that information from the model.
How do we do unlearning in the case of machine?
Yeah, there's this memory-based or gradient-based approaches. It's also a big literature, but yeah, I don't know if they can write me on Slack. I can maybe share a few pointers if you're interested. Yeah.
Okay, if there are no more questions, let's thank Beyza
Thank
again
you.
for the great talk.
Yeah.
Okay. Okay, so we'll take a break now until 4 p.m. and then we have the second tutorial of the school on mechanistic interpretability. And we keep the same splits as yesterday. Now we do have AC in the other room as well, so hopefully everything will be nicer today. Okay, thank you.
test, and I don't think it's working yet. Oh no, it is working yet. Great, the test is over.
Should I test it?
No, but basically you can just stand here and test, test, test. 1, 2, 3.
Yeah.
That's it.
Testing, talking somewhat louder, just to test that the microphone works. Nothing more than a test of the microphone. Don't worry, nothing is happening.
If you want to make a pause, something, just press this button.
Cool, makes sense. Hello. This is the Congress hall, that's right. Sarajevo Hall is the other one. Thanks. So if I zoom in, I won't open it, but it has like answer there, and all of these should have code that works. Doesn't have code or it doesn't work, that's a bug, so do flag it. But obviously we recommend you don't just look at the solution immediately, because it's like a learning experiment. But if you do, so the answers are all in the like drop down. Yeah, they're not like they shouldn't be. They should be closed by default. So, good question. Should be. Or is LaTeX you have to search for question mark? No, it's fine.
Hi, everyone. Please take your seats. We're going to start. Yes, please close the door. Yes, close the door. Okay, so very exciting to start the second tutorial of the school on mechanistic interpretability. That will be led by Arthur Conmy, who is a research engineer in DeepMind and an expert in interpretability. So yeah, have fun hacking. Thank you.
Yeah, I'll do it. I'll fix it after this. All right, okay. Hopefully everyone can settle down and get a laptop. Today is going to be the mechanistic interpretability tutorial day, and as mentioned, thanks so much, I'm Arthur. I'm a research engineer at DeepMind, and I work on interpretability. And there's like a collab today for you to go through, which hopefully has like something for people who like have no idea what mechanistic interpretability is and don't know what's happening, but also is like somewhat useful for the folks who know exactly what that means and think they have like some idea of how to do this stuff. We have some like extensions at the end, so I hope that it's good for everyone, but please do pass on feedback if that's like not true. And yeah, I'm not going to spend too much time talking, but just to kind of like set the scene for like, what are we doing today? What is the point of this kind of research area? And also like how this kind of notebook differs to what you've done yesterday and might differ to what you do otherwise. I will clarify those two things quickly. So yeah, this is on mechanistic interpretability. What is mechanistic interpretability? This is the area of machine learning that works on trying to reverse engineer and to more generally just find out how neural networks work in terms of their internal components. So this is pretty different to quite a lot of the other talks that are on specific kind of like applications and like new methods in machine learning. We're here taking kind of existing methods and trying to like understand how they work at all. And we have a number of exercises that take you through how you can even get access to the insides of like neural networks, and we'll be looking at large language models for the whole of this tutorial. And then we even have some exercises at the end that go through a kind of demo of what's called Golden Gate Claude, not with the real Claude model, which is like proprietary and from Anthropic, but this was a kind of famous demo from last year, or not that window, which you might have seen, but there was briefly a demo from Anthropic of a version of their Claude model that would always talk about the Golden Gate Claude, no matter what happened in the prompt. And if you haven't seen this, I'd recommend looking at some of the interactions online. It's quite funny, but there's a very small scale, but a replication of this at the end of the notebook, so there's something hopefully that's useful for everyone to get from this tutorial. And yeah, that's a brief overview of mechanistic interpretability. I have the link to the session in the second window I have open here at the bottom, which you can probably find in the Slack as well. And one point of clarification on the exercises is that all of the solutions are inside this kind of notebook. They're just hidden in drop-downs. So if I look at an exercise here, there's an answer drop-down. You can see just there on the screen, and if you click the answer drop-down, that will give you the full solution, so don't look at that unless you're like ready to move on, but it's all there. There's no like in a second notebook. I won't open that now. Yeah, I'll check in from time to time at this stand to talk through some solutions or things that come up, but I'll mostly be walking around, and you should also totally talk to all our TAs who are working today around the outsides of the room. If you have a look, they're standing up now, I think, and those people will be extremely helpful for helping you with issues you have. And yeah, you'll want a GPU, so like a T4, which you can see at the top corner on Colab, and if that doesn't work, I think you go, once you've made like a copy of this session, you go like runtime, change runtime type to T4 GPU there. But if there's an issue, just stick a hand up and a TA can come round. But I don't want to talk too much. I want to do some coding and like have everyone have a good time on the notebook. So yeah, link at the bottom. I'll keep my screen on for a while, but go ahead and try and get started with the notebook. And I'll check in a while once we have something to go through. T4. It will be required for the last part, definitely. You're welcome to try something else. It won't work for the last part, but it would probably work for the first part. I'll give it a go. some stuff with like a small language model, and I don't think that will fit on a smaller GPU. Yeah, that's right. Yeah. Oh, sure. Yeah, it's like T4 or bigger. Yeah, perfect. Yeah, yeah. Absolutely. free to message me. I'm on the Slack, so I'm going to probably give a talk, a bit of a chat now, but it seems cool work. Yeah, it's pretty weird. It's a very good point. Can you think of a reason why you get this result? But still, I agree with you, the proof is hard. Can you see what the reason is?
That's a pretty, I don't know, fixed, like, that might not extrapolate all the whole area of performances.
Yeah. Another way to phrase it, but you basically have the idea, is that that's a narrow distribution. Let's say there's a small distribution of prompts on which a head is like harmful. But if you look at like all the prompts of like the natural language distribution, it would be much more surprising that like deleting it is useful.
How the head changes, how the result changes, how the result of this experiment changes if we average the expected large number of prompts, or it would be like depending on the prompt theory that result will change.
Yeah, exactly. Like each set of heads is useful for different parts of like the prompts. It's definitely the case that like some heads matter way more than others. I'm not saying like every head is useful or whatever, but like yeah, if just removing the head improves performance, if you think about it from the perspective of gradient descent, probably gradient descent we just learned to like delete the head,
Yeah,
not useful. So like it's basically impossible for there to be a head, which if you delete it just improves performance everywhere. Because like otherwise why wouldn't gradient descent have like removed it? Does that make sense?
Yeah, that makes sense. Also, like, this probably explains. I also wanted to like not ask a question from Zora, which I understand very well now. For example, the identity themselves. Well, no, you
Yeah. Not always, but sometimes it will.
but why? Even if you put the sense of why the loop unit itself.
I would presume that it's not like I don't know a critical thing not used to do with the token itself, because like looking at the same token can be done by the MLPs and other parts of the network, so it's not really important. My guess is obviously you need to actually study this to like do the experiments and what we find out. My guess is that just like earlier training for some reason it was useful for that head to return to itself, whatever, and then later parts of the network relied on that head returning to itself. You see what I mean?
Yeah, I see.
And so once you have like a head which is turning to be boring, the later part of the network depends on it. You see what I mean?
Yeah.
It's difficult for gradient descent to learn to like delete the earlier parts. Yeah. Because like we don't have any algorithms that do like really smart like engineering of like the exact hits you need. So my guess is that's what's happening. It's just kind of fragile.
But the programming environment then is for there is a smarter way to figure out at the point at which movement is good. You could probably delete this head in a smart way, so to make other parts of the model independent of this head.
Yeah.
That's a good example.
Yeah, I think that can work. Yeah, and for what it's worth, there are some pretty neat stuff that work quite well. Like there's a good paper I can try and find in the chat where they show that you can actually like delete roughly half of llama's attention layers, just like can remove them, and the performance is worse, but like it's basically the same. So like there's enormous amounts of just like redundancy probably.
I know, as a matter of fact, all the small models are trained by training the biggest model, correct? Are going to the small models train the big model, then you stick in smaller models, and you get much more room to get marginal change in performance. That basically is also an example.
Yeah, that's possibly. I feel it's a different. Okay, that like proves that it's large I'm going to go through one of the exercises that when I was walking around came up several times. So if you've already done this, then feel free to just press on with the work. If you haven't done this, I guess we will go through it now, so sorry for the spoilers. But this was on this exercise where we have the layer 0 pattern from Q and K work. And a thing that repeatedly came up, I just went through it so I had it fresh in my brain, but you can obviously look at the solution when you want to. A thing that came up was people were confused about asking why we were applying a triangular mask. Like, why would we do that inside a transformer? And so sorry if I've already given this explanation to you, but I thought it'd be good to say it to everyone. So why are we applying the triangular mask? The idea is we want to train transformers for language in the first place in order to predict next tokens. So you can have a chatbot that's really good at generating a bunch of next tokens so it can give you an answer to a question. And in order to make a model that can learn to predict the next token in a sentence, it's important that we don't allow the model to just cheat, if that makes sense. If we say to the model, you have a sentence, it's I went to the shop, 5 words, for example, 5 tokens, and you allow the model at the position, for example, I went to to see that the next token is shop or whatever. So if we didn't have this triangular masking, what would happen is it would allow the transformer to learn, the way I predict the next token is I look at the next token and I copy that back into this current position. So the reason why the sentence goes, I went to the shop, is, well, the shop is just there. I can look at it. So the idea is it's really important that when we're training these models, we don't allow them to just look into the future to see what the next tokens are, because otherwise they wouldn't learn anything interesting about what the next tokens are on new queries. They'd only be able to just memorize what existing sequences are, probably. I'm not 100% certain what you'd learn if you got a transformer like that, but it definitely wouldn't be very useful. So the idea here is the query is the part of the attention calculation. The query is the part which is where should I attend to? And then the key vector is the vector we're going to dot with that to determine how much we should attend to each position. And so the idea here is that it's important that the query can't be dotted with the future positions, so that it's not possible to get the query attending to the future positions. It's fine for it to attend to the same position, because in the transformer, when you have again, to stay with the sentence, I went to the shop, for example, it's totally fine that I went to the. The model can look at the current position of the and go the sentence says I went to the. What should I say next? We have the word the. It's probably a noun. Could be the shop. Could be I don't know, the park. I went to the, could be anything after that. So it's fine to look at the token. It's just really important we don't look at the next token because that would allow the transformer to cheat. And so one way you can implement this is, I think I had this hook Q, and sorry, my code is probably messier than the solution, but I want to do it from scratch. And you have this hook K, and it's important that we say the hook Q part, I did this with some a-range torch function, that this is going to be greater than or equal to the hooked Q value effectively, which says the query needs to be at least as big as the query index will be at least as big as the key index. And one thing that I'd recommend doing, which I'll try and, live code here, is that this code gives you this layer 0 pattern from cache. So I'd recommend looking at the layer 0 pattern from cache. So this is 12 and then 33 by 33. There are 12 heads per layer in this transformer. So if we print out the attention pattern for the first head, what we see here is that 1 you see there that's followed by loads of zeros. That says for the first token, there's just 1 attention to the current position, because there's always attention that sums to 1, and at the 0, the very first position, there's nowhere it can attend to apart from itself, because otherwise it would be cheating looking into the future. And you can see it the second position, there's only attention to the first 2 positions, and it's 0.96 and 0.03. These add up to 1. The rest of the positions are 0 until you get to the very last token, the very last position. This is attention everywhere. So this is probably somewhat of an ugly way I get to the solution, but you can read probably the exact solution for the clean way to do this, and hopefully that gives some intuition about what the triangular mask is doing and why it's there. There's one last note. If you've worked with a transformer called BERT, there are other transformer variants, and there's also vision transformers. These will often look at all positions, but when you think about language, when you think about like what you want like ChatGPT or any language model to do, it should, like, if you think about it for a moment, be clear that it's important that like ChatGPT doesn't know in advance what the next tokens are going to be. It needs to be doing prediction. So when you use it for like applications, like things you do in your life, that it doesn't like that is able to, sorry, like guess what the next token is, even on completely new situations. There was a good question, which was? Yeah, that's a good question, which was, is this just like all highly dependent on what the language model application is, or like transformer application? For example, the example was given, if we want to do some just analysis of a large block of text, and maybe we produce some score output or something, it would be totally valid to just have attention going everywhere, and then the neural network computing a value. I think that like the way the like language model research has gone is that people more and more want to like have long and many tokens for generation. So there's a technique which you might have heard of called chain of thought, which is where you allow a language model to produce many tokens in a row to like think out loud. So it will say, I have this problem. What am I going to do to solve this problem? Here are the parts of the problem. And chain of thought, which produces many tokens one after the other, it's important for an application like that that we train the model so they don't know what's coming in the future, so they generate kind of like original thought effectively. Yeah, that's kind of the world I live in. I work a lot on language models, but it's totally correct that, yeah, vision transformers, old language models like BERT, and like applications like, I've got a block of text and I want to score out of it, those wouldn't require this kind of like triangular masking. Mm-hmm. Yep, there's a good question on bidirectional attention. So there are transformer variants as well, adding to the list of vision transformers, transformers to output a score, and old trials transformers like BERT, and now bidirectional attention transformers nowadays as well. You can do tricks that make the like prompt, the query you send to the user, have like attention going everywhere. But all of this is like a new form of transformer, and you can certainly get chat models that are trained solely with this triangular part here. But yeah, totally right. more minutes, so you might want to skip on to the last bit if you haven't already. I'm still happy to take questions and stay around for a while if it's useful.